There is a star in our sky that doesn't merely shine, it glows, as if the cosmos itself dipped a brush into garnet and painted a flame onto the void. Mu Cephei, the Garnet Star, is a forgotten jewel of the northern night, a red supergiant so vast it could swallow our solar system whole, yet so distant that its light takes thousands of years to reach us. It is a living monument to the life and death of stars, a quiet giant nearing its final breath. But even in death, it holds the power to shape new worlds. This is the story of a star on the edge of oblivion. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The name, Garnet Star, is no exaggeration. Even to the unaided eye, Mu Cephei radiates a noticeable ruddy glow when viewed under a clear, dark sky. While most stars blend into the cosmic canvas, Mu Cephei dares to differ, pulsing with the intensity of a slow-burning ember at the edge of perception. When seen through a telescope, this effect is amplified. An almost surreal cherry-red brilliance beams from its distant sphere, captivating those lucky enough to gaze upon it. The garnet color isn't a poetic flourish. It's real, physical, and scientifically explainable, though few stars show it with such vivid intensity. But why does it glow red? Why not blue or white, like the majority of luminous stars? Its hue comes from its nature. It's a red supergiant, one of the largest types of stars in the universe, and its outer layers are relatively cool by stellar standards. That cooler temperature, around 3700 Kelvin, means that it radiates light primarily in the red and infrared parts of the spectrum. Where hotter stars emit more blue or ultraviolet light, Mu Cephei, in its vast and bloated form, glows with the heavy warmth of cooling iron. It is a star in the twilight of its life, and its coloration is the quiet herald of its nearing end. What makes the Garnet Star so visually compelling is not just its color, but its ability to inspire. For thousands of years, humans have assigned meaning to the colors of the sky. A red moon is an omen. A red sunset is a poem. And a red star, a rarity, becomes legend. It's not hard to imagine ancient observers being drawn to it, mystified by its hue and unsure of what it meant. In the modern age, astronomers have studied its spectrum, classified its type, and attempted to measure its distance, but the sheer visual impact of Mu Cephei still remains something that transcends data. It connects to emotion. When British astronomer William Herschel viewed Mu Cephei through his telescope in the late 18th century, he was so struck by its color that he described it as a very fine deep garnet-colored star. That description stuck, and with good reason. There are many red stars in the sky, but few so intensely saturated that even visual observers from centuries ago remarked on the depth of color. The name, Garnet Star, does not come from mythology, nor from science. It comes from pure, raw impression. Herschel's words capture the essence of what it means to be moved by the cosmos, to see something so beautiful and alien that only a comparison to earthly gemstones could suffice. To look at Mu Cephei is to see starlight transformed into color. Not simply light traveling across 2,800 years to reach us, but light bathed in time, cooled by distance, and shaded by age. It's like looking into the dying fire of a cosmic furnace, a place where atoms once forged in nuclear fury now drift outward into the void, cooled and fading. This star doesn't burn with youthful heat, it radiates maturity, decline, and the inevitable peace that follows a long life well lived. Unlike the crisp blue of a young, searing star, Mu Cephei's red glow is diffused and mellow. It suggests vastness and slowness. It pulses not with frenetic energy, but with ponderous dignity. It does not flare quickly, it dims and brightens with slow, deliberate rhythm, like a sleeping giant breathing in its slumber. The star is dying, yes, but it's doing so with grace, and with beauty. And this is why Mu Cephei captivates astronomers, astrophotographers, and poets alike. It is a rarity in color, size, and symbolism. It's the red lantern in the celestial wilderness, a guidepost to the terminal majesty of massive stars. To study it is to observe what happens when the largest of stars prepare for their final act. To see it is to remember that even endings can be beautiful. To locate Mu Cephei in the vast dome of the night sky is to embark on a journey through myth and geometry, charting your course by patterns that have guided explorers, storytellers, and astronomers for millennia. While many stars fade into anonymity amidst the crowded sky, Mu Cephei has earned its place not only by brilliance, but by residence. It dwells within a storied constellation, a region rich with mythology, wonder, and significance. To find the Garnet Star, we turn our gaze to the northern skies, where the celestial king himself holds court. Mu Cephei is nestled within the constellation Cepheus, one of the 88 officially recognized constellations and among the oldest known. Named after the mythical king Cepheus of Ethiopia, husband of Cassiopeia and father of Andromeda, this constellation has been mapped by humanity since the time of the ancient Greeks. It lies high in the northern sky, a fixture of the circumpolar stars for those living in northern latitudes. This means it never sets below the horizon in many regions, especially across most of Europe, Canada, and the northern United States, making it a permanent, though sometimes overlooked, resident of the night. The constellation itself isn't one of the most visually striking. Cepheus doesn't blaze like Orion or sprawl like Hydra. It's more subtle, consisting of a pentagon-shaped pattern that loosely resembles a house or crown. But hidden within that modest geometry is Mu Cephei, one of the most remarkable stars in the entire sky. And once you know where to look, it becomes impossible to ignore. To find Mu Cephei, begin by locating Cassiopeia, the easily recognizable W or M-shaped constellation nearby. From Cassiopeia, trace a line toward another northern giant, Polaris, the North Star. Somewhere between the elegant zigzag of Cassiopeia and the steady anchor of Polaris lies the house-like figure of Cepheus. Within this outline, you'll find Mu Cephei positioned on the eastern edge of the constellation. It doesn't align with the brightest stars, but if you scan carefully in a dark sky, that rich reddish dot will eventually catch your eye, and when it does, there's no mistaking it. Astronomically, Mu Cephei carries the Bayer designation, Mu, because it was once thought to be the 12th brightest star in its constellation, according to the original Bayer classification. But that ranking belies its visual impact. Despite the letter, Mu, being associated with lower brightness compared to alpha or beta stars, Mu Cephei can appear surprisingly bright, especially when its variable luminosity is near maximum. Its ruddy color makes it even more distinct among the more typical white and blue stars nearby. What further aids its visibility is its proximity to interesting neighboring celestial landmarks. Mu Cephei lies not far from the famous Elephant's Trunk Nebula, in the constellation of Cepheus, and is situated in a rich part of the Milky Way. When scanning this area through binoculars or a telescope, the starfield appears densely packed, with Mu Cephei often standing out like a ruby buried in silver sand. Because of its location, Mu Cephei also enjoys nearly year-round visibility in the northern hemisphere. In summer, it hovers high overhead in the late evenings. In fall and winter, it descends slightly but remains visible for long stretches of the night. Its relatively constant presence in the sky makes it an ideal target for amateur astronomers hoping to witness the star's changing brightness and hue over time. For those south of the equator, however, Mu Cephei can be more elusive. It lies far enough north in celestial coordinates that it dips close to or below the horizon from many southern locations. This makes it a northern hemisphere treasure, a sky gem gifted to stargazers who endure the cold northern nights to see something truly extraordinary. Understanding where Mu Cephei lies is more than just spatial astronomy, it's also temporal. When you find the star, you are looking not just across space, but across time. Its light has traveled for approximately 2,800 years before reaching your eyes. That means the photons hitting your retina tonight left the Garnet Star around the time iron tools were first being widely used in Europe, and while ancient empires rose and fell on Earth, the light continued its silent journey across the void. Thus, locating Mu Cephei is not only a visual achievement, but a personal connection to cosmic history. Every glance upward becomes a communion with the past, a reminder that the heavens we admire are not frozen in time, but are in fact living records of celestial evolution and cosmic age. When we ask how far away Mu Cephei truly is, we're not just throwing a number into the black velvet of space. We're peering through layers of mystery, distortion, and cosmic dust to catch a glimpse of a reality that's elusive even with our most advanced tools. The current estimate places Mu Cephei at a staggering distance of approximately 2,800 light-years from Earth. But as with many things in the universe, the story behind that number is anything but simple. To begin, let's put that distance into perspective. A single light-year is nearly 5.88 trillion miles, 9.46 trillion kilometers. Multiply that by 2,800, and you get a distance so vast that it strains comprehension, about 16,464 trillion miles away. This means that the light we see from Mu Cephei tonight actually left the star during the height of ancient Greece's Archaic period. When early philosophers were beginning to ponder the universe, the photons from this star were already on their journey across interstellar space. What we see now is an image frozen in time, a snapshot of a celestial giant from nearly 3 millennia ago. But determining that distance hasn't been easy. In fact, the distance to Mu Cephei has been one of the most uncertain and debated aspects of its study. Why? Because Mu Cephei is surrounded by thick clouds of gas and dust, some of which it has ejected itself. These layers of cosmic fog absorb, scatter, and distort the light traveling toward us, making it difficult for astronomers to measure with traditional optical methods. Historically, one of the main tools for calculating stellar distances has been the parallax method, a technique that measures a star's slight positional shift against more distant stars as Earth orbits the Sun. This method works well for nearby stars, but with Mu Cephei, that shift is minuscule, nearly impossible to detect clearly with ground-based telescopes due to its sheer distance and the effects of intervening material. In recent years, the European Space Agency's Gaia mission has revolutionized our ability to chart stellar distances by providing extraordinarily precise parallax data for over 1 billion stars. Gaia has been instrumental in narrowing down the possible distance to Mu Cephei, though even Gaia struggles with stars like this, whose outer atmospheres are extended and variable, and whose light is filtered through thick veils of dust. Gaia's best data still suggest a distance in the range of 2,400 to 3,200 light-years, with 2,800 being a widely accepted median estimate. Even so, astronomers continue to cross-reference different techniques to improve the accuracy. One such method involves comparing Mu Cephei's luminosity and temperature to models of red supergiant behavior, and then adjusting for the amount of light lost to interstellar and circumstellar dust. By combining Gaia parallax data with spectral analysis and infrared observations, scientists refine the distance measurement in increasingly narrow bands. Still, every refinement carries a range of uncertainty because of how dynamic and complex red supergiants are. One of the reasons the distance is so important is because it directly affects our understanding of Mu Cephei's size, brightness, and future. If the star were significantly closer or farther than we think, all our calculations regarding its luminosity, radius, and mass would shift accordingly. A small adjustment in distance can mean the difference between a star that's merely huge and one that's among the largest ever recorded. And with an object as mysterious and influential as Mu Cephei, every detail matters. The incredible distance also reminds us of just how far light can travel, and how slow it really is, relative to the scale of the universe. While light seems instantaneous to us in daily life, in cosmic terms it is still bound by speed limits. The light we see from Mu Cephei tonight began its journey 2,800 years ago. Since then, civilizations have risen and fallen. Entire languages have been born and gone extinct. The pyramids were already ancient, the Roman Empire was yet to be founded, and yet the light from this single star has traveled patiently across the galaxy to finally meet your eye. It's also worth noting that Mu Cephei resides in the Milky Way galaxy, meaning it's still a local member of our galactic neighborhood, though clearly situated toward the more distant fringes of what we might call the inner spiral arms. It's located in the direction of the galactic plane, where the density of stars and gas increases. This is partly why there's so much dust and interstellar material in its direction, further complicating our ability to peer clearly at the star. As we stand on Earth and look up, knowing that Mu Cephei is 2,800 light-years away should instill a sense of both humility and wonder. It is a cosmic reminder that even within our own galaxy, the distances between stars are vast beyond comprehension. And yet, thanks to the persistence of science and the brilliance of modern technology, we can still measure and understand the faint echoes of giants who burn far away in the darkness. Mu Cephei is a red supergiant, and not just any red supergiant. It's one of the most colossal, awe-inspiring, and enigmatic members of this stellar class in our entire galaxy. To truly grasp what that classification means, we need to explore what happens when a star begins to reach the limits of its lifespan, how mass dictates a star's destiny, and why red supergiants like Mu Cephei are not only rare but also among the most important players in the life cycle of the cosmos. Let's start with the basics of stellar classification. Stars are categorized using a system known as the Harvard Spectral Classification, which organizes stars based on their temperature and the characteristics of their spectra. This classification system runs from hot, blue stars to cool, red ones, O, B, A, F, G, K, and M, with O being the hottest and M the coolest. Mu Cephei falls into the M spectral class, specifically M2, M4I, meaning it's a cool, red, and exceptionally luminous supergiant star. The IA designation places it in the upper echelon of supergiants, hyperluminous behemoths that radiate immense energy despite their relatively low surface temperatures. But temperature is only part of the story. What truly sets red supergiants apart is their evolutionary status. Stars like Mu Cephei began their lives much like other massive stars, burning hydrogen in their cores through nuclear fusion. For the vast majority of a star's life, this process is stable and efficient. In this phase, called the main sequence, the outward pressure generated by fusion balances the inward pull of gravity. However, for stars with initial masses greater than about 8 times the mass of the Sun, this balance doesn't last forever. As hydrogen fuel in the core becomes depleted, fusion halts at the center, and the core begins to contract under gravity. This contraction increases core temperature and pressure, igniting helium fusion in a shell around the core. At the same time, the outer layers of the star expand dramatically, cooling as they do so. The result is the red supergiant phase, a stage characterized by enormous size, relatively cool surface temperatures, 3,500, 4,000 K, and extraordinary brightness. That's where Mu Cephei currently finds itself. Red supergiants like Mu Cephei are among the largest stars in the universe in terms of volume, though not necessarily in mass. The reason for this is the expanded outer envelope, essentially a bloated, diffuse layer of gas that has swelled to hundreds, or even over 1,000 times the radius of the Sun. Despite their cool surface temperatures, these stars are tens to hundreds of thousands of times more luminous than the Sun, thanks to their sheer surface area. Mu Cephei in particular is estimated to be 1,000 to 1,650 times the radius of the Sun, placing it among the top tier of red supergiants in our galaxy. This massive expansion comes at a cost. The outer layers of the star become increasingly unstable, making red supergiants prone to pulsations, irregularities in brightness, and the shedding of huge amounts of stellar material. In fact, Mu Cephei is surrounded by a significant envelope of gas and dust, created by these very processes. Its atmosphere is so extended and diffuse that traditional stellar boundaries become almost meaningless. The photosphere, the layer from which the majority of light is emitted, can shift and fluctuate, making precise measurements extraordinarily difficult. Another defining trait of red supergiants is that they're short-lived by cosmic standards. While smaller stars like the Sun can burn for billions of years, red supergiants live only for a few million years. Mu Cephei is likely in the final million-year stretch of its life, if not far closer to the end. In this phase, the core is undergoing advanced stages of fusion, burning heavier and heavier elements, carbon, neon, oxygen, silicon, in a cascading sequence of shell fusion layers. Each new stage of fusion lasts for a fraction of the time of the one before. By the time a star like Mu Cephei begins fusing silicon into iron, it's living on borrowed time, possibly just days away from a cataclysmic end. But Mu Cephei isn't just an academic case study, it's a stellar archetype. Its classification as a red supergiant helps astronomers understand how massive stars evolve, how they interact with their environments, and how they eventually die. Red supergiants are the final act in a stellar narrative that ends in some of the most dramatic events in the universe: supernova explosions that scatter enriched material across the cosmos. These explosions seed future stars, planets, and even life, with the heavy elements they've forged in their cores. Studying stars like Mu Cephei also gives scientists insight into the mass loss processes of evolved stars. Red supergiants shed enormous amounts of material through powerful stellar winds, sometimes ejecting entire shells of gas and dust that can be observed in infrared and radio wavelengths. This material plays a crucial role in galactic ecology, contributing to the birth of new stars and the chemical enrichment of the interstellar medium. Mu Cephei is particularly important because it exemplifies the transition from a massive hydrogen-burning star to a helium and heavy element-burning colossus. It is no longer creating energy in the way the Sun does. Instead, it's layering its core like an onion, building up heavier and heavier elements that are inching it closer to gravitational collapse. When the core eventually becomes dominated by iron, an element that can no longer yield energy through fusion, gravity will win, and the core will implode in a spectacular supernova. In terms of observational characteristics, red supergiants like Mu Cephei show broad spectral lines and complex features in their light curves due to their massive, turbulent atmospheres. They often vary in brightness and temperature, and their surfaces can be covered in giant convection cells, huge, slow-moving currents of plasma that dwarf anything we see on the Sun. These convection currents create non-uniform brightness, which can make the star appear to flicker or change shape over time. The sheer scale and instability of these stars challenge our instruments and our theories alike. They force us to re-examine how stellar physics operates at extreme scales, and they serve as natural laboratories for testing our models of stellar evolution. Every detail we learn from Mu Cephei helps refine our understanding of how the universe creates and destroys stars, and how it recycles their remains into new generations of cosmic phenomena. In summary, Mu Cephei's classification as a red supergiant means it is one of the largest, brightest, and most evolved stars in our galaxy. It is nearing the end of a dramatic life story that will culminate in a powerful supernova explosion. Its enormous size, cool temperature, and turbulent outer layers make it a prototype for this stage of stellar evolution. As it continues to evolve, shed mass, and pulsate in its dying breath, Mu Cephei remains a crucial subject for astronomical study and a poignant reminder of the violent beauty of the cosmos. Mu Cephei is a star living on borrowed time, a cosmic titan slowly winding down the final acts of its luminous existence. It stands as one of the clearest examples of a massive star approaching the end of its evolutionary journey, teetering on the edge of one of the most violent and transformative events in the universe, a core collapse supernova. When we say Mu Cephei is nearing its end, we're not referring to days or years in human time, but to the grand astronomical clock. In cosmic terms, Mu Cephei is very old. In fact, it's dying. Massive stars like Mu Cephei evolve very differently from stars like our Sun, whereas our Sun will spend about 10 billion years on the main sequence calmly burning hydrogen in its core. Stars like Mu Cephei race through life with staggering speed. The very thing that gives them their brilliance, their massive supply of nuclear fuel, also ensures they burn it rapidly. For stars with masses over 8 times that of the Sun, the main sequence is just the beginning of a short and tumultuous life. Mu Cephei likely began its life with a mass between 25 and 40 times that of our Sun. During its prime, it would have been an intensely hot, blue-white O-type star, blazing with ultraviolet radiation and stripping away its outer layers with intense stellar winds. But once the hydrogen in its core was exhausted, gravity began to crush the core inward. The sudden rise in temperature and pressure ignited helium fusion, and with that came the star's expansion into the red supergiant phase. This is where we find Mu Cephei today. The red supergiant phase is not a peaceful retirement, it's a chaotic, unstable period marked by structural changes, core collapse preparation, and relentless internal fusion reactions. At this point in its life, Mu Cephei has a core layered like an onion, each shell fusing heavier elements than the one before. In its outermost shell, hydrogen is still fusing into helium. Beneath that, helium is fusing into carbon. Deeper in, Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. This series of fusion layers, each burning for a shorter duration than the last, is a telltale sign that a star is reaching its final moments. To illustrate, hydrogen fusion may last millions of years, helium fusion perhaps a million more, but silicon fusion, once ignited, lasts only a few days. Why? Because iron is the endpoint. It cannot release energy through fusion. In fact, attempting to fuse iron consumes energy. This dooms the star. When the core fills with iron, fusion stops, and gravity has no opposition. At this stage, Mu Cephei's outer layers have expanded into an enormous, loosely bound envelope of gas, and the star sheds material at a remarkable rate. This ejection of mass forms vast clouds of dust and gas around the star, much of which is detectable in the infrared spectrum. It's a stellar death shroud, and Mu Cephei wears it like a fading monarch slowly dissolving into its own legacy. This stellar aging process is unstable. Pulsations in brightness, irregular surface activity, and intense convection from deep within the star all signal a system under immense strain. The outer layers are so extended and tenuous that they are no longer bound tightly to the core. In many ways, Mu Cephei is dissolving into the surrounding interstellar space, one breath at a time. Another telltale sign that Mu Cephei is nearing its end is its variability. Stars in this late stage often experience irregular pulsations due to changes in temperature and internal structure. These pulsations don't just cause fluctuations in brightness, they also redistribute mass and energy, destabilizing the outer envelope even further. This is not a quiet process. It's a star actively unraveling, trying to hold itself together as the forces within its core push and pull against the fabric of its structure. Meanwhile, in the depths of its core, the real countdown has already begun. The star is currently burning elements like oxygen and silicon in a desperate final attempt to delay the inevitable. But this can't continue forever. Once the iron core reaches a critical mass, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, it can no longer support itself against gravity. When that limit is breached, the iron core collapses in a fraction of a second, triggering an explosive rebound that blows the outer layers of the star into space. This is the core collapse supernova. For a star like Mu Cephei, that collapse will happen swiftly and dramatically. In a matter of seconds, its core will crush into either a neutron star or possibly a black hole, depending on the remaining mass. The shockwave from the collapsing core will race outward, heating the star's envelope to billions of degrees, and igniting a supernova explosion visible across galaxies. At that moment, Mu Cephei will briefly outshine its entire host galaxy, releasing as much energy as the Sun will produce over its entire 10 billion-year lifespan, all in a single flash. So when we say Mu Cephei is nearing its end, we're not being poetic, it's a literal description of its current state. It has burned through nearly all of its usable nuclear fuel. It's shedding its outer layers, creating a halo of dust and gas that obscures its true size and brightness. And deep within, its core is on a relentless path toward collapse. It may happen tomorrow, or it may take another 100,000 years, an eye blink in astronomical terms, but it will happen. And when it does, it will be a moment of cosmic transformation. The elements forged in Mu Cephei's furnace, carbon, oxygen, silicon, and beyond, will be blasted into space, seeding the galaxy with the building blocks of new stars, planets, and potentially, life itself. This is how the universe recycles. Massive stars like Mu Cephei don't just die, they detonate in a final, glorious act that breathes new life into the cosmos. Mu Cephei's journey to this point has taken millions of years. It has been a brilliant, tempestuous life, filled with powerful radiation, violent winds, and deep fusion processes. And now, it rests on the precipice, trembling under the weight of its own gravity, held together by forces that are moments away from collapse. It's a star writing the last lines of its life story, one shell of fusion at a time. To witness Mu Cephei now is to gaze upon a dying ember of galactic fire, a relic of the universe's most powerful and ephemeral creations. To grasp the size of Mu Cephei is to stare directly into the vastness of the cosmos, and feel the scale of the universe push back at you. This is not just a big star, it is a staggering leviathan, an entity so vast that human comparisons feel almost absurd. Mu Cephei has a radius that exceeds 1,000 times that of our Sun, and possibly even more, depending on the latest observational refinements. At its maximum estimated radius, it could be as large as 1,650 solar radii, which would make it one of the largest stars ever recorded, if not in sheer mass, then certainly in volume. To even begin to comprehend this size, let's place Mu Cephei next to our own solar system. If you were to replace the Sun with Mu Cephei, its outer edges would reach far beyond the orbit of Jupiter. In fact, depending on the precise radius, since measurements vary slightly, it could easily extend past Saturn's orbit, engulfing Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, and perhaps even Saturn. Imagine every planet we know swallowed within a bloated, crimson envelope of hydrogen and helium gas. Earth would not merely be a speck, it would be vaporized in the heart of this gargantuan star. In raw distance terms, the radius of Mu Cephei is over 1.15 billion kilometers, or over 700 million miles. That's the kind of number that defies any direct intuitive understanding, so let's explore some creative comparisons to give this behemoth some human scale. Suppose you boarded a commercial jet airliner flying at 900 kilometers per hour, about 560 miles per hour, and you began a journey along the surface of Mu Cephei, circling its perimeter like a planetary tourist. To complete a single lap around its surface at that speed would take you over 5,000 years. That's a flight that would have to begin before the construction of the Great Pyramid of Giza, and would still be in progress today. Now imagine light itself, which travels at a blistering 299,792 kilometers per second, 186,282 miles per second. Even at light speed, it would take nearly 4,000 seconds, over an hour, to travel from one end of Mu Cephei to the other. By contrast, light takes only 8 minutes and 20 seconds to travel from the Sun to Earth. This fact alone underlines the monstrous dimensions of this star. You could fit more than 2,800 suns side by side across Mu Cephei's diameter, like pearls on an impossibly long necklace of fire. To bring it down to a more tactile level, if the Sun were the size of a standard basketball, Mu Cephei would be a sphere over 100 feet in diameter, roughly the size of a 10-story building. In that analogy, Earth would be smaller than a pinhead orbiting that basketball, now completely vaporized and lost inside the Crimson Colossus. Or picture this: if Earth were a grain of rice, the Sun would be about the size of a soccer ball, and Mu Cephei would be a hot air balloon the size of a football stadium. The scale is so dramatic that it breaks our intuitive grasp of distance and size. Even more incredibly, Mu Cephei is not even the largest star discovered. There are a few that may exceed it in radius, such as UY Scuti or VY Canis Majoris, depending on how they are measured, but Mu Cephei still remains a titan, one of the few stars so enormous that it would displace the entire inner solar system if placed where the Sun is. Its massive outer envelope is not solid or even stable, it's a tenuous, fluctuating atmosphere that stretches across space in deep red opacity. The outer layers are so distended that they are barely gravitationally bound to the star, and in fact, material from the surface is constantly drifting away, forming a halo of dust and gas. That's part of the reason why we cannot say with absolute precision how large Mu Cephei is. Its outer boundary is diffuse, and it breathes in and out over time, swelling and contracting like the lungs of a giant. Its volume is so extreme that it could contain billions of Earths. Some estimates place the volume of Mu Cephei at 1.65 billion times that of our Sun, which in turn is already 1.3 million times the volume of Earth. That would mean Mu Cephei could contain over 2.1 quadrillion Earths if it were hollow, and you were somehow able to pack them inside. Another way to think about it, if we could somehow line up Earth-sized planets in a grid inside Mu Cephei, you could build rows and columns of over 10,000 Earths in every direction, and still not reach its surface. These comparisons are more than just mind-boggling trivia. They underscore the incredible physical limits that stars can reach in their final stages of life. Mu Cephei's size is a result of its internal fusion processes generating enough outward pressure to counteract the immense pull of gravity. But this equilibrium is unstable. The same forces that make the star expand are also destabilizing it, spreading its mass over a vast space and making it vulnerable to eventual collapse. This is the paradox of red supergiants. They are majestic in their scale, yet ephemeral in their lifespan. Stars this large simply cannot last long. The more massive they are, the faster they burn. Mu Cephei is the astronomical equivalent of a candle burning at both ends, shining brightly but destined to vanish in a cosmic blink. So when we look at Mu Cephei in the sky, faintly glowing with its deep red hue, we're not just seeing a star, we're seeing a sphere of destruction and transformation, a giant whose body stretches across unimaginable distances, housing the turbulent storms of nuclear fusion and the whisper of death. It is a monument to scale itself, a red palace in the sky whose walls could encase the whole of our planetary neighborhood, and whose final breath will scatter the dust that may someday form new stars, new planets, and maybe even new life. The poetic name, the Garnet Star, has captivated generations of stargazers, and it traces back to one of astronomy's most influential figures, Sir William Herschel. Herschel, a pioneering 18th-century astronomer best known for discovering the planet Uranus, was also a master observer of the deep sky. At a time when telescopic astronomy was just beginning to flourish, Herschel's keen eye and curiosity about the heavens led him to notice something uniquely mesmerizing about a particular star in the constellation Cepheus, a star that shone with a red unlike any other. When Herschel gazed upon Mu Cephei through his telescope, he was struck not just by its brilliance or its size, but by its extraordinary color. He famously described it as having the deepest garnet hue he had ever seen in the night sky. Garnet, a precious gemstone known for its rich, crimson tones, perfectly matched the striking appearance of the star. Thus, Herschel began referring to Mu Cephei simply as the Garnet Star, and the name has endured ever since. This name wasn't just scientifically accurate, it was artistically resonant. In the 18th and 19th centuries, astronomy still held a poetic relationship with nature and the divine. Observers didn't just record the motions of the stars, they experienced them. For Herschel, who often brought a lyrical dimension to his observations, describing Mu Cephei as a garnet imbued it with personality and splendor. He wasn't just categorizing a point of light, he was honoring its unique visual essence. To understand the context, consider that most stars visible to the naked eye are white, blue-white, or yellow. True red stars are relatively rare in the night sky, and most are too dim to be seen without magnification. But Mu Cephei was a spectacular exception. Even to the naked eye under dark skies, it exhibits a deep reddish tint, an unusual and memorable quality for any celestial object. Through a telescope, that hue intensifies dramatically. To Herschel, who often used custom-built reflectors to sweep the heavens, the brilliance of this ruby-toned beacon would have been arresting. It's worth noting that the tradition of naming stars based on color was not new, but Herschel's label stands out because it wasn't merely a description, it was an emotional reaction. Garnets were considered not only beautiful but also symbolic of strength, passion, and enduring vitality. The legacy of the name, Garnet Star, speaks to how early observers blended science with sensation. Herschel was a meticulous data collector and a groundbreaking thinker. He coined the term asteroid, developed new telescope designs, and classified thousands of double stars and deep sky objects. Yet even he could not resist the emotional pull of such a vivid sight. Naming Mu Cephei after a gem wasn't frivolous, it was reverent. He recognized that this was no ordinary red dot in the sky but a celestial jewel, suspended in the firmament. Interestingly, the garnet-like appearance of Mu Cephei varies subtly with atmospheric conditions and observing tools. On some nights, it looks more like a smoldering ember, on others, it blazes with a radiant blood-red hue. These fluctuations only deepen the star's mystique and help reinforce its title as something precious and rare. Amateur astronomers today still report how seeing Mu Cephei through binoculars or a telescope evokes a sense of wonder and beauty unlike almost any other star, thanks to that unforgettable garnet glow. The name has also helped preserve Mu Cephei's identity outside of just catalogs and coordinates. Many people might forget or confuse designations like Mu Cephei, HD 206936, or KIP 107259. But the Garnet Star sticks in the mind. It's a name you remember, one that paints an immediate mental picture. In a cosmos full of cold numbers and technical descriptors, this poetic moniker makes the star feel more intimate, more human, and more emotionally alive. Astronomy, after all, is as much about awe as it is about accuracy. Herschel's contribution here was not just observational, it was also cultural. He gave us a star we could imagine holding in our hand, a cosmic jewel glowing in eternal twilight. The Garnet Star stands today not only as one of the most massive red supergiants in the sky, but as a reminder of how the night sky can move us not just scientifically, but poetically. The remarkable redness of Mu Cephei is not just a trick of the atmosphere or a poetic illusion, it's a direct manifestation of the physics playing out in the outer layers of one of the largest stars we've ever seen. When we look up and see the Garnet Star glowing like an ember in the blackness of space, what we're witnessing is the result of a complex interplay between its immense size, low surface temperature, and the particular spectrum of light it emits. To truly understand why Mu Cephei is so red, we need to journey into the core of stellar physics and unravel the science behind its signature hue. First, let's begin with the surface temperature, which is the most crucial factor. Mu Cephei has a surface temperature of about 3,700 Kelvin, significantly cooler than stars like our Sun, which has a surface temperature of approximately 5,778 Kelvin. And while 3,700 K is still incredibly hot by earthly standards, hot enough to vaporize most materials instantly, it is considered relatively cool in the context of stellar temperatures. Now here's where it gets fascinating. The color of a star is directly related to its surface temperature, as described by Planck's law and the blackbody radiation curve. Hotter stars emit most of their energy in the ultraviolet and blue wavelengths. These stars, like Rigel or Sirius, appear white or bluish-white to the naked eye. Cooler stars, like Mu Cephei, emit most of their energy in the infrared and red parts of the electromagnetic spectrum. As a result, the light we receive from Mu Cephei is dominated by long wavelengths, especially deep reds. This is why Mu Cephei has such a deep crimson appearance. Its spectral energy distribution is skewed heavily toward the red and near-infrared, giving it that garnet glow. Its low temperature compared to other stars means that photons emitted from its photosphere, the outermost visible layer of a star, fall within that reddish wavelength range. But there's more than just temperature at play. Another factor contributing to its intense red hue is molecular absorption in its atmosphere. Mu Cephei has a vast, extended atmosphere full of cool gases and molecules, including titanium oxide (TiO). This compound, common in the atmospheres of red giants and red supergiants, absorbs blue and green wavelengths of light more efficiently than red ones. As these shorter wavelengths are filtered out, the red and infrared light dominates what we observe from Earth. It's as though the star has built-in filters that selectively let its red light shine through, making it appear even redder than its surface temperature alone would predict. Moreover, the sheer size of Mu Cephei amplifies this effect. With a radius more than 1,000 times that of the Sun, the star's outer layers are so spread out that their density is extremely low. Light passes through vast shells of cooler gas, which also serve to absorb and scatter shorter wavelength photons. This scattering diminishes the contribution of any residual blue or white light and enhances the impression of a uniform, deep red glow. In fact, astronomers note that Mu Cephei's extended atmosphere is almost like a shroud, one so voluminous and diffuse that it creates a sort of natural dimming or reddening effect. This phenomenon, known as circumstellar reddening, arises because the material expelled from the star, dust and gas, can absorb and scatter blue light as it travels toward us. Even without an interstellar dust cloud in the way, Mu Cephei's own expelled matter acts like a veil, filtering and emphasizing the red tones of its emission. Interestingly, when viewed in infrared light, Mu Cephei reveals even more about its complex and dramatic nature. Infrared telescopes can peer through the dusty surroundings and capture the fuller picture of its luminosity. In infrared wavelengths, it becomes an even more dominant presence, far outshining most stars in the night sky. This ability to glow so intensely in the infrared reinforces just how much of its energy is emitted at those long, warm wavelengths. There's also a psychological aspect to the perception of its color. Human eyes are relatively less sensitive to red light in low-light conditions, which is why very red stars like Mu Cephei often stand out dramatically against the cooler, wider backdrop of the Milky Way. Under dark skies, the contrast is even more stunning. Through binoculars or a modest telescope, observers often describe the color as ranging from crimson to ruby to deep blood red, depending on conditions and equipment. The color can seem to deepen and glow more richly as you spend time observing it, much like your eyes adjusting to candlelight. Mu Cephei is also part of a rare class of stars that manages to emit color vivid enough to be noticed unaided. Most stars appear white or slightly yellowish to the naked eye because our eyes aren't good at detecting subtle color differences at low light levels. But the Garnet Star breaks that rule. Its redness is unmistakable even without a telescope, especially when viewed under dark skies with minimal light pollution. That alone makes it a rarity in the celestial sphere. Altogether, its red coloration is the result of a confluence of physical attributes: a relatively cool surface temperature, strong molecular absorption features that suppress blue light, scattering effects from its massive outer envelope, and layers of circumstellar dust that reinforce the reddish tint. When combined, these features create a star that doesn't just look red, it looks like it was born from fire itself. The vivid color is not just a cosmetic trait, it's a signal of its advanced evolutionary state. Stars like Mu Cephei don't start out red, they evolve into it. In its earlier life, Mu Cephei would have shone blue or white as a hot, massive star on the main sequence. But as it exhausted its hydrogen and began fusing heavier elements in its core, it expanded, cooled, and began to shed its outer layers. The red light we see now is the result of a star bloated and burdened by its own age, shedding light as it slowly moves toward a catastrophic demise. So when you look up and see the Garnet Star bleeding red into the night, you're witnessing not just a distant sun, but the grand finale of a giant. It is a colossal torch in the cosmos, burning in slow motion, sending out waves of crimson light as it readies itself for one last act. A supernova that will one day shatter its garnet shell and scatter its brilliance across the galaxy. When we speak of brightness in astronomy, it's important to draw a line between how bright something appears from Earth, its apparent magnitude, and how bright it truly is, its absolute luminosity. In the case of Mu Cephei, the difference is immense. To the naked eye, it appears as a dim, deep red dot, barely among the brightest stars in the night sky. But in truth, this crimson ember is one of the most luminous stars we know of. If placed next to our sun, it would utterly outshine it, drowning it out like a searchlight next to a candle. So how bright is Mu Cephei really? The answer: tens of thousands of times more luminous than our sun. But that number doesn't even begin to convey the sheer magnitude of energy involved. Let's break it down to understand why this red supergiant glows so ferociously, even at a surface temperature of just 3,700 K. Our Sun, a G-type main sequence star, radiates at about 3.828 times 10 superscript 2 watts. That's the energy of roughly a trillion 100 watt light bulbs all shining at once. Mu Cephei, by contrast, emits somewhere between 38,000 and 350,000 times that amount, depending on the specific study or model used. This wide range reflects the complex uncertainties in measuring the star's exact distance, mass, and radius. But even at the lower end of that estimate, we are dealing with a truly titanic force of light. So why does a cooler star outshine the sun by so much? The answer lies in size and surface area. Luminosity, according to the Stefan-Boltzmann law, is proportional not only to the fourth power of a star's temperature but also to the square of its radius. While Mu Cephei is much cooler than the Sun, it compensates for this lower temperature with sheer surface area. Its radius is over 1,000 times greater than the Sun's, meaning its surface area is millions of times larger. Imagine a vast cosmic furnace, radiating energy across a surface so enormous that it defies imagination. Even though each square meter of Mu Cephei's surface gives off less energy than the Sun's due to the cooler temperature, the sheer number of square meters more than makes up for it. The final result? A monster of a star whose total output of light and energy rivals the power of an entire galaxy's worth of suns scattered across space. But Mu Cephei doesn't just glow, it glows with a spectrum that favors red and infrared light. That means much of its true brilliance is hidden from our eyes, which are less sensitive to infrared wavelengths. When observed in visible light, it's still impressive, but when astronomers peer at it in the infrared, its luminosity explodes into full view. This is why early assessments of Mu Cephei's brightness often underestimated it. It simply wasn't shining most of its light in the visible range we are used to observing. To better grasp this, let's imagine moving the Sun and Mu Cephei to the same distance from Earth, say, 10 parsecs, about 32.6 light-years, and comparing their apparent magnitudes. Our Sun would have an absolute magnitude of plus 4.83, while Mu Cephei's would be around -7 to -9, depending on the luminosity model you accept. That's over 10 magnitudes of difference, which translates to the star being about 10,000 times brighter in terms of light energy. Put another way, if Mu Cephei replaced the Sun in our solar system, Earth would be vaporized in an instant, and the solar system would be bathed in red light so powerful that even Pluto would experience solar heat comparable to that of Mercury today. Its sheer radiance would stretch far beyond what any planets could safely orbit. It would be less a star in our sky, and more a crimson wall of fire consuming the heavens. Mu Cephei's brightness is also a direct clue to its massive interior processes. Deep inside, nuclear fusion is proceeding at a furious pace, fusing heavy elements far beyond hydrogen and helium. This furious energy production is necessary to support the star's massive outer layers from collapsing under their own gravity. And it's a temporary process, like a fire burning too hot too fast. Mu Cephei shines so brightly because it is in the endgame of its life, throwing off vast quantities of energy as it hurtles toward its inevitable collapse. In addition, Mu Cephei's luminosity is not steady. Like many red supergiants, it is a semi-regular variable star. Its brightness fluctuates over time due to pulsations in its outer layers. These expansions and contractions alter the star's radius and temperature, which in turn affect how much energy it emits. At times it dims, at others it brightens, all according to internal cycles that are still being actively studied by astronomers. Despite this variability, its average output remains mind-boggling. Even if Mu Cephei were located 100 times farther away than it is, over 280,000 light-years, it would still likely be visible with a modest telescope. That's the scale of its intrinsic brightness. We can also compare Mu Cephei to other supergiants to highlight how it stands among giants. For example, Betelgeuse, the famous red supergiant in Orion, has a luminosity somewhere between 90,000 and 150,000 times the Sun's. Mu Cephei, depending on the model used, exceeds this and comes close to titans like VY Canis Majoris or UY Scuti, though those have even larger radii and somewhat uncertain mass and brightness profiles. But unlike some of those stars, Mu Cephei's visual redness and brightness are uniquely striking, even without instruments. Its luminous output is also critical to how it interacts with its surroundings. The intense light pressure from Mu Cephei exerts radiation pressure on its outer layers, contributing to the ejection of stellar material into space. This process creates vast clouds of circumstellar dust and gas, which scatter and absorb some of the star's own light, producing further variations in observed brightness. It's like a giant lantern gradually smoking itself out with the very fire it generates. All told, Mu Cephei is not just bright, it is blindingly, unstoppably radiant, pouring out energy at a level nearly incomprehensible by human standards. It's a dying giant, burning its final fuel reserves in a last gasp of brilliance before the inevitable collapse. And as it does, it lights up the universe in crimson hues, not with the delicate flicker of a fading ember, but with the furious glow of a star writing its own cosmic epitaph in light. Mu Cephei is more than just a massive red beacon in the sky, it is a living, breathing titan. Unlike our Sun, which burns with a steady consistency, Mu Cephei is subject to subtle but powerful changes that make its brilliance dance across time. These shifts in brightness aren't random. They are rhythmic, like the breath of something ancient and vast. This phenomenon, its changing luminosity, is a result of pulsations within the star's outer layers, earning Mu Cephei the title of a pulsating giant. At its core, Mu Cephei is a supergiant of extreme size, mass, and energy. But with such a vast outer envelope, an atmosphere stretched across more than 1,000 solar radii, instability is inevitable. This atmosphere is not static. It expands and contracts in a cyclical pattern, driven by the dynamics of internal energy transfer and pressure changes within the star. These periodic movements are what cause the fluctuations in its brightness that we observe from Earth. Here's how it works. Deep within Mu Cephei, nuclear fusion is furiously churning elements into heavier ones. The immense energy created by this process pushes outward, trying to escape the gravitational grasp of the star. This pressure causes the outer layers of Mu Cephei to swell. As the outer envelope expands, it cools, dims, and slows its outward motion. Then, gravity wins for a moment, the expansion halts, and the layers begin to contract inward again. The compression raises the temperature, increasing the energy output and, therefore, the star's brightness. Once again, the intense pressure causes another expansion. This cycle repeats over weeks, months, and even years. Mu Cephei's pulsations are not perfectly regular, but they are patterned enough to classify it as a semi-regular variable star. Its apparent magnitude can shift between about plus 3.4 and plus 5.1, meaning that at times it is clearly visible to the naked eye, and at others it fades into the backdrop of fainter stars. These changes are typically not dramatic enough to be noticed from night to night, but over the course of weeks or months, careful observation reveals a clear ebb and flow in brightness. What's truly fascinating is that these pulsations are not limited to a single frequency. Mu Cephei, like many red supergiants, appears to oscillate in multiple modes simultaneously. In other words, different layers of the star might be expanding and contracting at different rates. This complex ballet of movement is what gives rise to the semi-regular variability. It's not as rhythmic as a metronome, but it follows a kind of cosmic music with overlapping beats. These pulsations are more than just a curiosity. They are a critical diagnostic tool for astronomers. By studying how the light of Mu Cephei changes over time, scientists can infer details about the internal structure of the star, such as its density, temperature gradients, and even the way energy is transported from its core to its surface. This field of study is known as astroseismology, the science of listening to the oscillations of stars to learn what's inside them. In addition to brightness, the pulsations of Mu Cephei may also subtly affect its radius and surface temperature. As the outer envelope expands, it cools slightly, and the star emits more in the red and infrared part of the spectrum. When the star contracts, it heats up slightly, pushing more of its energy output back into the visible spectrum. These variations are minute on a temperature scale, perhaps only a few hundred degrees Kelvin, but over the colossal surface area of a red supergiant, even small changes result in large differences in observed brightness. Another consequence of these pulsations is the gradual but significant mass loss. As Mu Cephei swells and contracts, its outer layers become increasingly unstable, allowing particles and gases to escape the star's gravitational grasp. Over time, this contributes to the formation of the dense circumstellar dust shell that envelopes Mu Cephei, an important factor in obscuring its light and making precise observations more challenging. One of the most intriguing aspects of Mu Cephei's pulsations is their unpredictable variability in amplitude and period. Unlike classical Cepheid variables, which pulse with extremely regular timing, Mu Cephei's cycles are more chaotic and sensitive to changes in the star's internal structure. This is likely because it is in a much later stage of stellar evolution and is inherently less stable. The irregularities in pulsation also suggest that the star may be transitioning between different internal fusion processes, perhaps switching from helium burning to carbon and heavier elements. Over the years, astronomers have monitored Mu Cephei's light curves, graphs that plot its brightness over time, and noted variations with long secondary periods as well. Some researchers believe that red supergiants like Mu Cephei may experience convective bursts, or cycles that cause broader scale variability over longer timescales, on the order of thousands of days. These longer-term brightness waves may be superimposed over the shorter-term pulsation patterns, creating a complex visual signature in the data. It's also worth noting that these pulsations are not simply the result of mechanical movement. They are also influenced by radiation pressure, stellar wind, and internal opacity shifts within the star. For example, when a region of the star's outer layers becomes more opaque due to changes in molecular density, it can trap more heat, causing localized expansion and luminosity shifts. This adds yet another layer of complexity to the process, making Mu Cephei a prime target for advanced astrophysical modeling and infrared monitoring. From the standpoint of human experience, these pulsations might seem slow. Cycles that unfold over hundreds of days are difficult to notice without long-term observation. But in the scale of stellar lifespans, this variability is a blink in time. These oscillations mark the unstable final chapters of Mu Cephei's life, warning signs of the cataclysm to come. In short, Mu Cephei is not a static monument of light. It is alive with motion, trembling with the struggle to hold itself together as its own immense mass tries to collapse in on itself. Every variation in brightness is a whisper from the heart of a dying star, echoing across the galaxy to be heard by anyone who cares to listen. Its light, pulsing through the void, carries with it not just illumination, but a story, a saga of gravity and heat, of expansion and collapse, of creation nearing its end. Mu Cephei's changing brightness isn't just a quirk, it's a coded message from the star's core. Classified as a semi-regular variable star, Mu Cephei exhibits a form of variability that lies somewhere between the steady pulses of classical variables and the chaotic flickers of irregular stars. This semi-regular variability offers astronomers a rare chance to glimpse the inner workings of one of the universe's most massive stars as it teeters on the edge of its final act. To understand what makes Mu Cephei a semi-regular variable, we have to begin by revisiting the concept of stellar pulsation, the expansion and contraction of a star's outer layers, much like the breathing of a colossal organism. For stars like Mu Cephei, these pulsations are driven by internal instabilities. Specifically, changes in opacity within the star's envelope, the outer gaseous layers, cause heat to build up, expand the atmosphere, cool it, and then contract again under gravity's pull. However, unlike more predictable variable stars such as Cepheids or RR Lyrae stars, Mu Cephei's pulsations are not clockwork. Instead, the star's brightness follows an irregular but discernible pattern. It may brighten over a few hundred days, fade slightly, then brighten again over a different interval. These cycles are not consistent in amplitude or duration, which is why it's considered semi-regular. In fact, its primary period is estimated to be somewhere around 730 to 860 days, but this period can shift, and it often has multiple overlapping cycles. Astronomers monitor these changes by plotting light curves, graphs of brightness over time. With Mu Cephei, these curves are gently undulating, showing rises and dips that suggest some underlying rhythmic process, but with enough variation to make modeling complex. These light curves are essential for deciphering what's happening beneath the star's surface. One reason for this semi-regular behavior is the incredible size and layered complexity of red supergiants like Mu Cephei. The interior of the star doesn't pulsate uniformly. Different layers may move at different rates. One layer might be expanding while another is contracting, leading to constructive and destructive interference that modifies the star's visible brightness in irregular ways. This dynamic layering also means that different modes of pulsation can be excited simultaneously. These are essentially distinct ways the star can vibrate, like how a drum head can thrum in multiple frequencies at once. In Mu Cephei, the fundamental mode might cause large-scale radial oscillations, the entire star swelling and shrinking, while overtones might involve more subtle movements in the outer envelope. In addition to these mechanical oscillations, convective motion, the boiling, turbulent movement of plasma in the star's outer regions, also plays a significant role. Red supergiants have enormous convective cells, much larger than those on the Sun. These cells churn slowly, carrying heat from the core outward. When a convective cell rises to the surface, it can brighten part of the star, and as it falls back, that region dims. Given the colossal size of Mu Cephei, a single convective cell can take years to cross the surface, contributing to long-term variability. This behavior is not random noise, it's rich with scientific information. The study of semi-regular variable stars like Mu Cephei helps astronomers understand how energy is transported in massive stars, how convection interacts with pulsation, and how mass loss may be initiated or accelerated. These insights are vital for refining models of stellar evolution, especially in the stages just before a massive star explodes in a supernova. Another key piece of information that astronomers extract from Mu Cephei's variability is related to mass loss rates. During periods of high luminosity, the star may emit strong stellar winds, shedding its outer material into space. Over centuries, this gradual ejection builds up a circumstellar shell of dust and gas. By studying how brightness changes correspond to mass loss events, researchers can better understand the pre-supernova conditions of red supergiants, how much material they lose, how fast, and in what direction. Semi-regular variability also offers clues about the star's interior fusion processes. As Mu Cephei burns through the last of its helium and begins fusing heavier elements like carbon and oxygen, it becomes increasingly unstable. This instability manifests in both structural changes and energy output, which can be traced through fluctuations in brightness. In some cases, dramatic changes in light output may even signal the onset of late-stage nuclear burning, such as carbon flashes, which are theorized to occur before core collapse. From a broader perspective, Mu Cephei's semi-regular variability places it in a special observational category. It becomes a stellar laboratory, a place where astronomers can test theories of astroseismology, probe the physics of turbulence and radiation pressure, and examine the subtle interplay between fusion, convection, and gravitational forces. Moreover, this variability isn't just useful to scientists, it's part of the star's poetic identity. The changing brightness of Mu Cephei is a visual symbol of its fragility and power. It is not a constant, eternal light like some stars. Instead, it pulses like a cosmic heartbeat, a visible sign that it is alive, evolving, and inevitably moving toward a climactic end. For amateur astronomers, Mu Cephei's variability can even be observed with the naked eye under dark skies. Tracking its changes over months offers a tangible connection to a star nearly 3,000 light-years away, a link between Earth-bound eyes and a supergiant's dying breath. In summary, Mu Cephei's semi-regular variability is more than a curious trait. It is the expression of profound physical forces at play within one of the most massive stars visible from Earth. By studying the way its light ebbs and flows, astronomers unlock secrets of stellar interiors, fusion dynamics, and the eventual fate of red supergiants. It's as if the star is telling us its story, one flicker of light at a time. Mu Cephei, for all its brilliance and grandeur, is a star that refuses to yield all its secrets. Despite centuries of observation and technological advancements in astronomy, this crimson titan remains shrouded in a veil of mystery, both figuratively and literally. The immense uncertainty surrounding Mu Cephei's distance, size, and internal dynamics stems primarily from one defining feature: its vast and complex outer atmosphere. Unlike many smaller or more stable stars, Mu Cephei possesses an extended and highly diffuse envelope of gas and dust. This envelope doesn't sharply end like a rigid surface. It fades away gradually into space, merging almost imperceptibly with the surrounding interstellar medium. That characteristic makes it nearly impossible to determine where the star's surface actually ends, and where its stellar wind begins. When we talk about the radius of Mu Cephei, we're not pointing to a well-defined boundary but rather estimating a value based on how deep we can see into the haze. This vagueness in its outer structure creates a chain of uncertainty. If we don't know exactly how big the star appears in the sky, then we can't precisely calculate its absolute radius, especially because that value also depends on how far away the star is. And therein lies the second layer of the mystery. The distance to Mu Cephei itself is not firmly known. Estimates have placed Mu Cephei at anywhere from 2,400 to over 3,000 light-years away from Earth. most recent studies, especially those incorporating data from the European Space Agency's Gaia mission, tend to support a distance near 2,800 light-years. However, even Gaia, which is designed to measure stellar positions with unprecedented precision, struggles with Mu Cephei. The sheer size and variability of the star, combined with the distortion caused by its dusty atmosphere, make accurate parallax measurements exceptionally difficult. The reason is that Gaia relies on measuring the tiny apparent shift in a star's position in the sky as Earth orbits the Sun, a method known as parallax. For relatively nearby or small stars, this shift is clear and measurable. But Mu Cephei's light is scattered and absorbed by dust, not just around it, but also in the interstellar space between it and us. This absorption, called interstellar extinction, skews the star's apparent brightness and colors, which in turn introduces error into models that try to calculate distance based on observed brightness, what we call spectrophotometric parallax. In other words, we are looking at Mu Cephei through a cosmic fog, both caused by its own dying breath and the dusty highway of space stretching across the thousands of light-years between us. That fog doesn't just dim the light, it alters its characteristics, causing infrared and red wavelengths to dominate while other wavelengths are absorbed or scattered. Thus, even its apparent redness is enhanced by the dust, making it hard to separate how much of the red hue comes from the star's temperature, and how much is caused by intervening material. This cloak of gas and dust also confounds attempts to directly image Mu Cephei. Observing stars involves measuring their angular diameter, how large they appear in the sky. For Mu Cephei, that diameter fluctuates based on the technique used, and on the wavelength observed. In visible light, the star appears smaller, because we can only see through the less obscured portions of its atmosphere. In infrared light, which penetrates deeper into the dust, Mu Cephei appears larger, sometimes significantly so. This discrepancy makes defining the star's true edge a scientific dilemma. Is the surface, where the optical depth equals 1? Or where emission falls below a certain threshold? There's no universal answer. One of the greatest consequences of this uncertainty is the difficulty in determining its true luminosity. Because luminosity depends both on brightness and distance, even a small error in measuring how far away the star is can lead to massive differences in the calculated energy output. Some models have placed Mu Cephei's luminosity as merely 30,000 times that of the Sun, while others go as high as 350,000 times. That's not just a discrepancy, it's a chasm in understanding. And it has a domino effect on everything from models of its internal fusion to predictions of its ultimate fate. Moreover, Mu Cephei's atmosphere is not static, it's dynamic and turbulent. Its pulsations, which we discussed earlier, generate massive outflows of material. These outflows are not evenly distributed either. Some regions shed more material than others. There is even evidence suggesting that giant convective cells, far larger than anything found in our Sun, dominate Mu Cephei's surface. These can cause one side of the star to appear brighter than the other, or shift the center of light away from the geometric center of mass. That imbalance plays havoc with high-precision astrometry, the branch of astronomy focused on positional measurements. It's also worth noting that Mu Cephei's variability in brightness can change the opacity of its atmosphere in real time. As layers expand and cool, they become more transparent or more opaque depending on their temperature and composition. This ongoing metamorphosis creates a blurring halo around the star when viewed through telescopes, sometimes masking or mimicking changes in size and brightness that may not be actual changes in the physical star at all. All of these factors make Mu Cephei a stellar puzzle of the highest order. While we can confidently say that it's one of the largest and most luminous red supergiants known, we must also admit that many of its fundamental characteristics are still wrapped in ambiguity. Astronomers are working diligently to pierce the fog, using adaptive optics, long baseline interferometry, and space-based observatories to improve precision. Each new generation of instruments gets us closer to Mu Cephei's true nature, but for now, it remains a celestial enigma, an awe-inspiring reminder that even the most radiant objects in the universe can harbor secrets within their glow. The mystery doesn't diminish its beauty. On the contrary, it deepens the sense of wonder. We are staring across nearly 3 millennia of light years at a dying giant, cloaked in the material it has shed, pulsing softly in the dark, whispering answers in wavelengths we are only beginning to fully comprehend. Mu Cephei is not only remarkable for its size and color, but also for the immense cloud of dust that envelopes it, a dusty shroud that both conceals and reveals the late-stage drama of its stellar life. As a red supergiant nearing the final chapters of its existence, Mu Cephei is engaged in an intense process of shedding its outer layers, casting vast quantities of material into the surrounding space. This ejected material condenses into a colossal and complex cloud of dust and gas, one that stretches far beyond the star itself, forming a sort of cocoon, an echo of its own mortality that dims its light and muddles its edges. This dust isn't merely a backdrop. It's a fundamental part of what defines Mu Cephei's current state and its eventual fate. The ejection of dust is not a calm, consistent release, it's an irregular, episodic process. Massive convective currents inside the star dredge up material from deep within, launching it outward in turbulent plumes that escape the star's tenuous gravity. These outbursts, driven by pulsations, radiation pressure, and large-scale atmospheric dynamics, carry carbon, oxygen, silicon, and other heavier elements synthesized in the star's fusion core. Once expelled, this gas cools as it moves away from the supergiant's scorching surface. As it cools, atoms begin to stick together, forming molecules, and eventually grains of solid dust. In the case of Mu Cephei, the resulting dust is primarily silicate-based, which is typical for oxygen-rich red supergiants. These grains can grow large enough to effectively absorb and scatter visible light, particularly blue and green wavelengths, which makes the star appear even redder than it truly is. This phenomenon adds to the deep garnet hue that William Herschel so famously admired, and complicates the interpretation of observations made through optical telescopes. This dust doesn't form a uniform sphere around the star. Observations suggest that it is asymmetric, possibly clumped into arcs, shells, or even long tails extending outward into space. The ejection events may not be isotropic. In other words, Mu Cephei might be shedding more material in one direction than another. Such uneven mass loss might be influenced by the star's rotation, magnetic fields, or internal oscillations. These dusty asymmetries have been revealed through high-resolution infrared imaging, which is able to pierce through the densest parts of the cloud and expose structural details that are otherwise invisible in normal light. In some ways, the dust becomes a time capsule. Because the material spreads outward at measurable speeds, often tens of kilometers per second, astronomers can calculate how long ago certain ejections took place. These expanding shells act like tree rings, preserving a timeline of Mu Cephei's dying breath. Studying these patterns helps researchers map the star's mass loss history, giving insight into how long the current shedding phase has lasted, and how much mass has already been lost. And the amount is staggering. Mu Cephei is estimated to lose material at a rate of around a few millionths of a solar mass per year, though some spikes can be much more extreme during periods of enhanced instability. Over tens of thousands of years, this amounts to several solar masses worth of material expelled into space. It's an unsustainable hemorrhage, one that speaks of imminent death. Eventually, this loss of mass will destabilize the star to the point where its core can no longer support the outer layers. That's the precursor to collapse, the moment when the supernova becomes inevitable. The dust cloud is not just a sign of dying, it's also a birthplace. The heavy elements within the cloud, carbon, oxygen, silicon, iron, are the very building blocks of planets, moons, and future stars. In time, long after Mu Cephei has gone supernova, this material will be recycled into new solar systems. The atoms born in the heart of this one giant star may one day make up the rings of a gas giant, the crust of a rocky planet, or even the cells of a living organism. Dust, in the cosmic sense, is not death, it is transformation. But for now, this dust creates problems and possibilities. For astronomers trying to study Mu Cephei, it is both a barrier and a beacon. In visible light, the dust absorbs and dims the star's brightness, making it appear smaller and redder than it truly is. In extreme cases, thick ejections can hide significant portions of the star entirely. But in the infrared spectrum, the dust becomes radiant. It glows with the heat absorbed from the star, acting like a lantern in the dark, outlining the extent of the cloud and providing clues about the composition and structure of the material. Instruments aboard the Spitzer Space Telescope and other infrared observatories have been instrumental in mapping this circumstellar dust, offering detailed snapshots of how Mu Cephei is dismantling itself. There is even speculation that dust production could accelerate in the final stages of Mu Cephei's life. As the fusion reactions in the core change character and grow more unstable, the star's outer layers may pulsate more violently, leading to sudden, massive eruptions of material. These eruptions could produce dense, short-lived clouds that rapidly evolve. If we are lucky and telescopes are trained on it at the right moment, we might witness one of these outbursts in real time, a kind of final exhalation before the end. Some of these dust clouds also extend beyond Mu Cephei itself, possibly merging into the larger interstellar medium. It's not just the star's immediate neighborhood that is affected. As this material drifts outward and disperses, it becomes part of the Milky Way's vast reservoir of dust and gas, the raw material from which stars and planets continue to form. In this way, Mu Cephei's death throes are not isolated but interwoven into the ongoing cycle of cosmic rebirth. There is a profound beauty in this. A star shedding its skin, one layer at a time, not in darkness, but in glowing halos of red and gold, visible across millennia of space. A dying colossus surrounded by the very substance that will outlive it, radiating not just heat, but the promise of future worlds. As Mu Cephei inches closer to its inevitable end, one question looms over its destiny like a ticking cosmic clock. Will it explode in a fiery death as a supernova? The answer, almost certainly, is yes. The physics of massive stars offers little room for escape from such a finale. When a star like Mu Cephei, immense, old, and unstable, reaches the end of its life, it no longer has the internal fuel needed to hold itself up against gravity. That balance collapses. And when it does, the result is one of the most powerful events in the universe, a core collapse supernova. To understand how this will unfold, we must first recognize what stage Mu Cephei is in. As a red supergiant, it has already completed the stable hydrogen-burning phase that defines the majority of a star's lifetime. It has fused hydrogen into helium for millions of years. Once that fuel was exhausted in the core, the star began fusing helium into heavier elements like carbon and oxygen. This cycle of nuclear fusion continues through progressively heavier elements, each new phase shorter than the last. At this moment, Mu Cephei is likely burning through elements such as carbon, neon, and magnesium in a frantic series of shell fusion layers surrounding an increasingly unstable core. Eventually, it will try to fuse iron, a process that spells doom. Iron fusion consumes energy rather than releasing it. This is where the star's struggle ends. Without the outward pressure generated by fusion to counteract the immense inward force of gravity, the core collapses in a matter of seconds. Electrons are smashed into protons, forming neutrons and releasing a flood of neutrinos, ghostly particles that carry away vast amounts of energy. The core becomes a neutron star, or possibly even a black hole if the mass is high enough. Meanwhile, the outer layers of the star, suddenly unsupported, fall inward and then rebound off the core in a cataclysmic shockwave. That shockwave, amplified by neutrino energy, blasts the star apart. This is the supernova. If Mu Cephei goes supernova, it will be one of the most spectacular events visible from Earth in recorded history. Though it lies some 2,800 light-years away, the explosion would shine brighter than a full moon in the night sky, possibly even casting shadows on Earth for days or weeks. Historical records of supernovae like SN 1054, which created the Crab Nebula, describe similar phenomena, a new star appearing suddenly and visible even during the daytime. In Mu Cephei's case, this visibility would be far more intense and enduring due to its sheer mass and size. The explosion would eject several solar masses worth of material into space at thousands of kilometers per second, forming an expanding shell of energized gas and dust that would glow in radio, optical, ultraviolet, and X-ray wavelengths. This nebula, an ephemeral remnant, would persist for tens of thousands of years, gradually cooling and mixing into the surrounding interstellar medium. Astronomers around the world would study the event in real time, using every telescope available, collecting data that would inform our understanding of stellar death and supernova mechanics for generations. But despite its inevitability, we don't know when Mu Cephei will explode. This could be tomorrow, or 100,000 years from now. Predicting the exact timing of a supernova is one of astronomy's greatest challenges. While certain precursor signs, such as increased variability in brightness, enhanced mass loss, or sudden temperature changes, might hint at an approaching collapse, none are definitive. Mu Cephei may be silently ticking away toward a moment that will reshape its region of the galaxy forever. The event will not only be a visual marvel, but a deeply physical one. The supernova will release more energy in a matter of seconds than our Sun will in its entire 10 billion year lifespan. Most of this energy will be carried away by neutrinos, but a fraction of it will power the expanding fireball that tears through the star's former envelope. The shockwave will compress, heat, and ionize the gas around it, sparking new waves of star formation in nearby clouds. The death of Mu Cephei could, quite literally, plant the seeds of stellar birth in a neighboring nursery of stars. There's also the matter of what gets left behind. If the remnant core is less than about 3 solar masses, it will form a neutron star, a city-sized sphere of matter so dense that a single teaspoon of it would weigh billions of tons. These neutron stars often spin rapidly and emit beams of radiation, becoming pulsars. If Mu Cephei's mass is sufficient, though, the collapse will go even further. Gravity will crush the core beyond the neutron degeneracy limit, forming a black hole, an object from which not even light can escape. If that happens, Mu Cephei's legacy would be one of total collapse, a transformation into a gravitational ghost that silently warps space and time. But long before that final collapse, the signs will intensify. Mu Cephei may become more erratic, shedding even more material, dimming behind thick veils of dust, flaring in unpredictable ways. Astronomers will continue to watch, analyze, and theorize, looking for subtle shifts that might suggest the end is near. The red giant's swan song could be a series of brief, explosive outbursts, precursor events, that herald the coming supernova. From a galactic perspective, this explosion will be a gift, enriching the interstellar medium with heavy elements like iron, gold, and uranium, which are only forged in the violence of such stellar deaths. Without supernovae like the one Mu Cephei will become, the universe would lack the raw materials for rocky planets, oceans, and biological life. In fact, every atom of calcium in your bones and iron in your blood was likely born in a supernova not unlike the one Mu Cephei is destined to unleash. And so, while we watch this brilliant red star shimmer in the constellation Cepheus, we are seeing not just a cosmic relic of the past, but a harbinger of future chaos and creation. Its quiet glow today is the last chapter of a story that began millions of years ago, a story that will soon erupt into one of the universe's most dramatic finales. The Garnet Star, so calm and poised in the sky, hides a storm beneath its surface, a storm waiting to be unleashed upon the galaxy. When Mu Cephei finally collapses in a catastrophic explosion, the nature of that supernova will depend on what remains in the star at the time of its death, specifically, whether it retains its massive hydrogen envelope. All signs point to it ending its life as a Type II supernova, the quintessential death of a red supergiant. These are the supernovae we most associate with the dramatic end of a massive star's life, luminous, prolonged, and often as majestic as they are violent. Type II supernovae are characterized by the presence of hydrogen in their spectra, a telltale fingerprint that distinguishes them from their stripped envelope cousins, like Type IB and Type IC supernovae, which have shed their hydrogen, and sometimes helium, layers before explosion. In Mu Cephei's case, it still appears to retain an enormous, extended outer shell composed largely of hydrogen. This means when the core collapses, that outer envelope will play a defining role in the explosion's structure and behavior. To understand the explosion type in detail, let's look at how Type II supernovae function. As Mu Cephei reaches the final moments of its life, its core will have a composition dominated by iron. Up to that point, fusion of lighter elements, like hydrogen into helium, helium into carbon, and onward through neon, oxygen, and silicon, has created increasingly heavier elements in concentric shells, somewhat like the layers of an onion. But iron represents a dead end. Fusion reactions involving iron consume more energy than they produce, which robs the core of its ability to support the star against gravitational collapse. At that point, the iron core, perhaps just over 1.4 times the mass of the Sun, the so-called Chandrasekhar limit, will collapse under its own gravity in a fraction of a second. Protons and electrons are smashed together to form neutrons, and neutrinos are released in a torrent of almost unimaginable power. This marks the formation of what might briefly become a protoneutron star, with an extremely high density and compact size. This collapsing core will then create a rebound shockwave when the imploding material slams into it. In theory, this shock should blow the outer layers off, but this alone often isn't sufficient. In modern astrophysics, we now believe that the flood of neutrinos from the collapsing core deposits enough energy into the star's outer layers to revive and strengthen the shockwave, allowing it to blow outward through the hydrogen envelope. That explosive departure of material is what becomes visible across the cosmos, a stellar death cry that can outshine the entire galaxy for days or weeks. Now, among Type II supernovae, there are several subclasses, and Mu Cephei is likely to end up as a Type IIp or possibly a Type IIl supernova. The P stands for plateau, describing the light curve of the supernova, how its brightness changes over time. In a Type IIp, after the initial brightening, the light stays fairly consistent, plateaus, for several weeks before fading. This plateau occurs because of the recombination of ionized hydrogen in the ejected material. Essentially, as the expanding hydrogen-rich envelope cools, electrons recombine with protons to form neutral hydrogen atoms, releasing energy and keeping the brightness steady. Type IIp supernovae are the most common variety of core collapse supernovae seen in the universe and are tightly associated with red supergiants like Mu Cephei. Its immense hydrogen envelope and apparent instability make it a textbook candidate. If the star were to lose more of its outer hydrogen before collapse, through powerful stellar winds or increased mass ejections, it might instead become a Type IIl supernova, where L stands for linear, because the light curve declines more steadily after the peak. What differentiates these explosions, however, is not just their brightness or duration, but the information they give us. The spectral lines and evolution of a Type II supernova reveal volumes about the internal composition of the star, the amount of material it has ejected, and the properties of the resulting neutron star, or black hole. For astronomers, a Type II supernova is like an autopsy of a massive star, conducted with light. Another intriguing feature of Type II supernovae is that they are often preceded by warning signs, an uptick in erratic behavior, large-scale mass loss, and increased brightness in the infrared as dust forms and is heated by the star's radiation. Mu Cephei already exhibits some of these characteristics, and as it grows more unstable, it may offer us a front-row seat to the prelude of stellar death. The ejected material from the supernova will move outwards at speeds of around 10,000 km per second, rapidly forming a supernova remnant. This cloud of debris will eventually blend into the interstellar medium, dispersing elements like carbon, oxygen, silicon, and iron, all forged during the star's life and explosive death. These elements are not just cosmic leftovers. They are the ingredients of planets, atmospheres, oceans, and life. In fact, the oxygen you breathe and the calcium in your bones were likely created in the same kind of supernova that Mu Cephei is destined to become. Finally, let us not forget the sheer cosmic visibility of such an event. A Type II supernova from Mu Cephei, located some 2,800 light-years away, would be a spectacle not seen in modern human history. It might rival the supernova of 1006 AD, or the more recent SN 1987A, but even brighter. It could remain visible to the naked eye for weeks or months. Astrophysicists would track its spectral lines, light curve, and expanding shock front in real time, using instruments across the electromagnetic spectrum. Every pulse of light, every shift in wavelength, would become a data point in the life and death of a star, and by extension, a lesson in how the universe makes and recycles its building blocks. So when Mu Cephei dies, it likely won't do so quietly. Its farewell will be thunderous, luminous, and violently beautiful, a Type II supernova to mark the end of one of the Milky Way's largest, reddest giants. And in that moment, we will witness not just the end of a star, but the rebirth of its elements into the galaxy, ready to take part in the endless cycle of cosmic creation. As we peer into the twilight years of Mu Cephei's life and ponder its explosive finale, the natural question that arises is, what will be left behind? After the fireworks of a Type II supernova fade, does the Garnet Star's heart survive, or does it collapse into the most enigmatic of cosmic phenomena, a black hole? To explore this, we must understand what determines the fate of a dying star. The key factor is mass, specifically the core mass that remains after the outer layers are expelled in the supernova. For Mu Cephei, a red supergiant of staggering proportions, this core is massive enough to place it on the brink between two starkly different afterlives, becoming a neutron star, or collapsing entirely to form a black hole. When a star dies in a core collapse supernova, its central regions implode under gravity, compacting protons and electrons into neutrons. If the remaining core is between about 1.4 and 3 solar masses, the neutron's degeneracy pressure can resist the inward pull of gravity, halting collapse and forming a neutron star, an ultra-dense object about 20 kilometers across, spinning rapidly and radiating intensely. However, if the core's mass exceeds this limit, estimated around 2.5 to 3 solar masses, depending on equations of state and how exotic the core's material is, then nothing known to physics can stop the collapse. Not neutron degeneracy pressure. Not radiation. Nothing. The core continues to shrink past the Schwarzschild radius, forming a singularity hidden behind an event horizon. A black hole is born. For Mu Cephei, estimates of its initial mass range widely but generally lie somewhere around 25 to 40 solar masses, maybe more. Throughout its life, Mu Cephei has shed an enormous amount of its mass through stellar winds and episodic mass ejections. These winds, often accelerated by the radiation pressure of the star's own photons, have carried away its outer layers, enriching the surrounding interstellar space with elements like carbon and nitrogen. But despite this mass loss, it is still believed that Mu Cephei's final core mass will be sufficiently large, quite possibly greater than 3 solar masses. This leads most astrophysicists to conclude that Mu Cephei is an excellent candidate to form a black hole. This doesn't mean its path is guaranteed. The final mass of the core, how much of the outer envelope is ejected during the supernova, and how much fallback occurs, material that initially is expelled but then falls back onto the collapsed core, will all influence whether the remnant becomes a neutron star or collapses further into a black hole. If enough fallback material is added to an already massive neutron star core, that alone could tip it over the mass threshold and trigger complete collapse into a black hole. Interestingly, simulations suggest that in very massive stars like Mu Cephei, the explosion itself might not be as complete as in lower mass stars. In some scenarios, the outer layers are ejected with less energy, and much of the star might fall back onto the core. This scenario is called a fallback supernova, and it could result in a black hole without a particularly bright or visible supernova display. In this case, Mu Cephei could disappear from the sky with relatively little warning or spectacle, an eerie, silent collapse. Alternatively, if the explosion is energetic and efficient at ejecting the outer layers, a bright and classic Type IIp supernova might occur, followed by the birth of a neutron star. But that outcome becomes less likely the higher the mass of the core, and current models lean toward black hole formation for red supergiants of Mu Cephei's magnitude. Now let's consider what kind of black hole Mu Cephei could form. Unlike the supermassive black holes at the centers of galaxies, this would be a stellar mass black hole, likely around 5 to 15 times the mass of the Sun. Its event horizon, or Schwarzschild radius, would be only about 15 to 45 kilometers across, but the gravity in its vicinity would be incomprehensibly strong. Not even light would escape it. Such a black hole would be undetectable unless it had a binary companion or accretion disk, which Mu Cephei does not appear to have. This means the black hole could remain completely invisible to us, a ghostly monument to the former star's grandeur. Astronomers would be left studying the aftermath of the explosion, the expanding cloud of debris, the missing light where the star used to shine, and the gravitational effects on surrounding gas and dust, to infer that a black hole had formed. In recent years, gravitational wave detectors like LIGO and Virgo have opened a new window into black hole science. If Mu Cephei were to collapse in a slightly asymmetric way, it could send out gravitational waves, ripples in the fabric of space-time, that might one day be detectable by these instruments, especially if the collapse was accompanied by a companion star or resulted in a brief neutron star phase before collapse. There's also the possibility, however rare, that Mu Cephei might form a magnetar, a type of neutron star with an incredibly powerful magnetic field, but this would require highly specific core conditions and an unusually high rotation rate, which does not currently appear to be the case for this slow-spinning red supergiant. Ultimately, the most probable scenario remains black hole formation. Mu Cephei is likely too massive, too far into its evolutionary journey, and too burdened with a collapsing iron core to halt the gravitational implosion with just neutron pressure. And in that final moment, after millions of years of slow burning, color shifting, and luminous radiance, the Garnet Star may end not with a whisper or a bang that we can see, but with an implosion so complete that even light itself cannot escape its grasp. A beautiful red light, once among the brightest in the northern skies, may vanish forever, leaving behind only the memory of its glow and the void where it once stood, a silent, invisible tribute to nature's ultimate act of compression. When we speak of Mu Cephei, we're speaking of a behemoth, but it is not a solitary giant in the cosmos. The universe is home to a class of similarly staggering red supergiants, and among them, names like Betelgeuse and VY Canis Majoris frequently rise to the surface. These stars, like Mu Cephei, represent the most massive and evolved members of the stellar population, all hurtling toward dramatic ends in supernovae. But each of them also has unique characteristics that distinguish them from one another, both in scientific terms and in the poetic light they cast on our night sky. Let's begin with Betelgeuse, one of the most well-known stars in the night sky. Located in the constellation Orion, Betelgeuse is a red supergiant much closer to Earth than Mu Cephei, about 642 light-years away, compared to Mu Cephei's estimated 2,800 light-years. This proximity is part of the reason Betelgeuse has fascinated astronomers and the general public alike. Its variability is visible to the naked eye, and it occupies a prominent place in modern culture. In terms of size, Betelgeuse is enormous, with a radius around 900 times that of the Sun, but Mu Cephei is often considered even larger, with estimates placing it at over 1,000 solar radii. That's enough to engulf the orbit of Jupiter, while Betelgeuse would stop closer to the orbit of Mars. However, it's important to recognize that these numbers are hard to pin down precisely, especially because both stars have extended, diffuse atmospheres that blend into surrounding interstellar space, making exact edge measurements elusive. Still, Mu Cephei tends to win in terms of color purity and visual intensity. Betelgeuse is more orange-red, while Mu Cephei is often described as a much deeper, richer crimson, hence its nickname, the Garnet Star. William Herschel, who coined that term, wasn't exaggerating. When seen through a telescope, Mu Cephei displays a hue unmatched by nearly any other star visible to the naked eye, giving it a uniquely dramatic presence in the sky. Betelgeuse is also a semi-regular variable star, like Mu Cephei, with fluctuating brightness caused by pulsations in its vast outer layers. But Betelgeuse's dimming episodes have drawn particular attention in recent years, especially its great dimming in 2019 to 2020, which some speculated was a prelude to a supernova. It turned out to be caused by a combination of pulsation and dust ejection, a behavior very similar to what Mu Cephei has been exhibiting for centuries. Both stars are shedding outer layers in preparation for their final acts, and both offer a unique laboratory for studying mass loss, stellar wind dynamics, and the pre-supernova evolution of massive stars. Now let's shift to VY Canis Majoris, an entirely different beast. While Betelgeuse is more famous, VY Canis Majoris is larger and more extreme. Located in the constellation Canis Major, it sits roughly 3,800 to 5,000 light-years away, and its radius is estimated to be a jaw-dropping 1,500 to 1,800 times that of the Sun, although again, this figure depends heavily on how we define the boundary of the star's diffuse outer layers. In terms of volume, that means if VY Canis Majoris were placed where the Sun is, it would stretch beyond Saturn's orbit, dwarfing even Mu Cephei. However, this vast size comes at the cost of stability. VY Canis Majoris is more chaotic than Mu Cephei, marked by irregular, violent mass loss events and enveloped in a vast cloud of gas and dust. It is often referred to as a hypergiant, a classification used for red supergiants that are even more massive, unstable, and bright than typical supergiants like Betelgeuse. VY Canis Majoris emits powerful stellar winds that carry away its outer layers at a furious pace, creating a surrounding nebula filled with knots, arcs, and filaments of material. This is where Mu Cephei and VY Canis Majoris align once again. Both stars are nearing the end of their lives, both are enshrouded in ejected material, and both are poised to die in spectacular fashion. In terms of luminosity, all three stars, Mu Cephei, Betelgeuse, and VY Canis Majoris, vastly outshine our Sun. Mu Cephei, for instance, is estimated to be about 350,000 times more luminous than the Sun in terms of total energy output. VY Canis Majoris, thanks to its extreme size and mass, can reach even higher outputs, potentially 500,000 times the luminosity of the Sun. Betelgeuse, although closer and more familiar, is the least luminous of the three, with luminosity estimates ranging between 100,000 and 140,000 times that of the Sun. Another important difference is how visible these stars are from Earth. Betelgeuse can be seen from both the northern and southern hemispheres, and it's bright enough to be one of the 10 brightest stars in the night sky. Mu Cephei, on the other hand, is fainter due to its greater distance and heavy dust absorption. It lies in the Cepheus constellation, which is a circumpolar constellation for many northern observers but never rises for far southern observers. VY Canis Majoris, in Canis Major, is visible mostly from the southern hemisphere or the southern parts of the northern hemisphere. So where does Mu Cephei stand among these stellar titans? It occupies a middle ground. It is larger than Betelgeuse, both in radius and in color intensity, but smaller than VY Canis Majoris, which stands near the theoretical limits of stellar size and mass. Mu Cephei is more photogenic due to its vivid garnet hue, yet less dramatic than the turbulent VY Canis Majoris. It is more mysterious than Betelgeuse, largely because it lies farther away, wrapped in layers of dust that challenge astronomers to unlock its secrets. But perhaps what makes Mu Cephei truly special isn't just its size or its color, it's how it fits into the broader story of stellar death and rebirth. It represents a classic case study of a red supergiant transitioning into the end phase of its life. It's bright, massive, variable, and layered in dust and history. It gives us a direct line to understanding how massive stars evolve, die, and recycle their material into the galaxy. In the company of stars like Betelgeuse and VY Canis Majoris, Mu Cephei is not an outlier but a member of a grand and solemn lineage, stellar monarchs nearing the end of their reign, destined to collapse and explode, leaving behind either a void or a neutron-rich ember. Together, these stars offer us a time-lapse of death and transformation on a scale that defies imagination, reminding us that even the grandest giants of the night sky are not eternal, but part of the ever-turning wheel of cosmic evolution. There's a common confusion that arises whenever Mu Cephei and Betelgeuse are mentioned in the same breath, and that confusion centers around which of the two is actually larger. The answer is layered and not as straightforward as most would like, because in astronomy, especially when dealing with red supergiants, size is a slippery concept. When we look closer, we begin to unravel how distance, atmosphere, dust, and the dynamic nature of these stars all contribute to the misunderstanding, and why Mu Cephei has often been erroneously underestimated. Let's start with the basic comparison. Both Mu Cephei and Betelgeuse are red supergiants, stars nearing the ends of their lives after having exhausted the hydrogen fuel at their cores. They have both expanded to enormous sizes, cooled at their surfaces, and begun to exhibit pulsations and mass loss. Betelgeuse is much closer to us, about 642 light-years away, while Mu Cephei lies at an estimated 2,800 light-years or more. That proximity alone gives Betelgeuse an unfair advantage in terms of study. We can resolve its disk, track its surface activity, and even model its turbulent convection zones in some detail. Mu Cephei, cloaked in its distance and its heavy veil of circumstellar dust, remains far more enigmatic. Now, when it comes to radius, the numbers often cited are eye-popping. Betelgeuse is generally measured to be about 887 times the Sun's radius, give or take, depending on which wavelength range and observation technique is used. Mu Cephei's radius, meanwhile, is estimated to be at least 1,260 times the radius of the Sun, and some estimates go up to 1,650 or more. If those higher estimates hold, Mu Cephei would indeed dwarf Betelgeuse, not just slightly, but significantly. However, these estimates are highly dependent on models of distance, brightness, and the amount of dust in front of the star. Even a small error in the distance to Mu Cephei introduces a large uncertainty in its derived size. What compounds this is that Mu Cephei's atmosphere is not sharply defined. Red supergiants like Mu Cephei have extended, diffuse atmospheres composed of ionized gas and expelled material that doesn't form a crisp boundary like the Sun's photosphere does. It's not like you can draw a circle around it and say, "Here ends the star." Instead, it's more accurate to say Mu Cephei has a core region with radiative emissions, surrounded by a semi-transparent atmosphere, and further surrounded by layers of dust and gas expelled through stellar winds. Betelgeuse is not immune to this problem either, but because it's so much closer, astronomers can resolve some of its outer layers using interferometry, giving them a better grasp on its diameter, even if that diameter also fluctuates slightly due to its pulsating nature. In contrast, Mu Cephei is like a dim, glowing ember seen through layers of fog from miles away. The farther it is, the more imprecise our measurements become, and the more likely we are to debate its actual physical extent. But that hasn't stopped comparisons, and in many astronomy texts and articles, Mu Cephei is regularly listed as one of the largest known stars, often ranked higher than Betelgeuse. That ranking is usually based on models that use its luminosity, temperature, and estimated distance to calculate radius, a standard method. Luminosity is directly related to a star's size and temperature, via the Stefan-Boltzmann law, so by knowing how bright Mu Cephei is and how cool its surface is, about 3,700 K, astronomers can back-calculate its size. Even with conservative estimates, Mu Cephei consistently comes out larger than Betelgeuse. This leads to an interesting public confusion. Because Betelgeuse is the more famous star, thanks to its place in the prominent Orion constellation and its visible fluctuations in brightness, many assume it must also be the largest, or at least among the top few. In reality, Betelgeuse is big, but it's not quite at the top of the red supergiant scale. Mu Cephei, though less known, stands a bit taller in cosmic stature. Another point of comparison is mass. Betelgeuse's mass is estimated to be between 11 to 20 times that of the Sun, depending on model and phase of evolution. Mu Cephei's mass estimates fall in a similar range, perhaps slightly more, around 19 to 25 solar masses. These numbers are rough, because again, we're dealing with stars that are shedding mass at enormous rates. Both Betelgeuse and Mu Cephei have likely lost a significant portion of their initial mass by now, so current mass values don't tell the full story of their lives. However, both are massive enough to eventually undergo core collapse supernovae, and possibly form black holes. In terms of visual appearance, Mu Cephei's red color is deeper and more intense than Betelgeuse's orange red. Observers have described Mu Cephei as looking like a glowing ember, the kind of deep red you might see at the heart of a fire, whereas Betelgeuse has a warmer, more orange hue. This difference is not just poetic, it reflects actual differences in spectral characteristics and surface temperature. Betelgeuse has a slightly higher temperature, around 3,600 to 3,700 K, whereas Mu Cephei is closer to 3,500 to 3,600 K, depending on where you measure it in its pulsation cycle. And yet, while Mu Cephei may be larger and redder, Betelgeuse is more accessible to science. It's one of the very few stars whose disk we can image directly, and it has been studied extensively in radio, optical, and infrared wavelengths. It's also been the subject of supernova watch speculation, particularly after its dramatic dimming event in 2019 to 2020. Mu Cephei, although likely headed toward the same fate, receives less attention primarily because it's harder to study. Its distance, and the heavy dust it has shed make it appear dimmer and less dramatic to the casual observer. But to the trained eye, Mu Cephei represents an equally fascinating and possibly even more extreme case of stellar evolution. In summary, yes, Mu Cephei is larger than Betelgeuse, at least by most current models and estimates. The confusion stems from our limited ability to observe Mu Cephei directly and the widespread familiarity with Betelgeuse. While Betelgeuse gets the spotlight, Mu Cephei looms in the background, bigger, redder, and even more enigmatic, a quiet giant cloaked in crimson and cosmic dust, waiting patiently for its final blaze of glory. Studying Mu Cephei presents a unique and persistent challenge to astronomers, even with the most advanced tools at our disposal. It's not that the star doesn't want to be observed, it radiates with the deep crimson glow of a dying colossus, but rather that nature itself conspires to obscure it. Its vast physical size, immense distance, and shroud of circumstellar dust create a layered puzzle that most telescopes struggle to solve, at least with clarity. To understand why this behemoth star is so elusive despite its raw brilliance, we must examine how size, dust, and distance create observational barriers. The first and most obvious problem is its sheer size. Mu Cephei is estimated to be more than 1,000 times the radius of our Sun, and possibly as large as 1,650 solar radii. If it were placed at the center of our solar system, it would stretch far beyond the orbit of Jupiter. But unlike compact objects like white dwarfs or neutron stars that emit sharp, well-defined signals, red supergiants like Mu Cephei have extended, fuzzy outer atmospheres. These are not clean spheres, they're diffuse, dynamic, and chaotic. Their atmospheres stretch far beyond the dense core of the star, creating a kind of blurry edge that resists easy measurement. In astronomy, we rely on resolving power, a telescope's ability to distinguish between two close points of light, to extract details from distant objects. But the further away something is, the smaller it appears in the sky. Despite its enormous size, Mu Cephei's great distance, roughly 2,800 light-years, means that it appears as just a tiny speck, even to many powerful telescopes. It occupies a very small angular diameter in the sky, too small to easily resolve without the help of interferometry or infrared imaging, and even those methods struggle when obscured by additional layers of material. That brings us to the second obstacle, dust. Mu Cephei is surrounded by a thick, dusty shell of material it has expelled over time. This isn't rare for red supergiants. In fact, it's a hallmark of their evolutionary stage. As these stars grow older, their outer layers become increasingly unstable. They start shedding mass through stellar winds at an astonishing rate, more than 1,000,000 times faster than our Sun. This material, hydrogen, helium, carbon, silicon, and other heavier elements, is pushed outward, creating a cocoon of dust that veils the star in the infrared and visible spectrum. This dust not only absorbs and scatters visible light, making the star appear dimmer and redder than it actually is, but it also re-emits that absorbed energy in the infrared, often creating a diffuse glow that confuses measurements. From Earth's perspective, much of this dust lies directly in our line of sight, and it can obscure important features like the star's outer limb, spectral lines, and even its precise shape. Telescopes that rely on optical wavelengths, like the Hubble Space Telescope, are particularly hindered. The visible light we receive is like looking at a sunset through a sandstorm, beautiful, but distorted and murky. Even if we shift our instruments to the infrared spectrum, where dust is more transparent, there are still hurdles. For one, Mu Cephei's environment is constantly changing. The star pulsates, its outer layers expand and contract, and the dust cloud continues to evolve. This means that any infrared image we take today may not represent the star's structure tomorrow. It's like trying to map a foggy coastline where the tide is always changing. We get fleeting impressions, but never the full picture. Furthermore, the problem isn't just the dust from Mu Cephei itself. There's also interstellar dust between us and the star, cosmic material floating throughout the Milky Way. This adds a second veil to the first, further dimming and reddening the light that reaches us. Astronomers must model and subtract the effects of this interstellar extinction, a complex process that introduces additional uncertainty. Estimates of Mu Cephei's true luminosity, color, and size must be adjusted to account for this filtering, and depending on which extinction model is used, the numbers can vary quite a bit. Then there's the problem of motion. Mu Cephei isn't static. Like most stars, it has a proper motion across the sky, and combined with its pulsation and mass loss, this makes it a moving, breathing entity. To track its changes over time requires consistent, long-term observation, and that's difficult to maintain with major observatories where telescope time is limited and competitive. Even space-based telescopes like the James Webb Space Telescope, JWST, face difficulty in capturing fine details of Mu Cephei because it is not one of the brightest or closest red supergiants, nor is it a top candidate for supernova monitoring like Betelgeuse. Therefore, it receives less priority in the global observation agenda. While it has certainly been observed, it lacks the wealth of high-resolution, time-resolved imaging that we have for more famous neighbors. All these factors combine to create a perfect storm of observational difficulty. Mu Cephei is enormous but distant, brilliant but obscured, important but understudied. Its faint red glow reaches us through a corridor of shifting gas and dust, flickering with variability and shadowed by uncertainty. It's as though the universe has placed a curtain between us and one of its most majestic actors, offering only glimpses, never a full reveal. Despite these challenges, astronomers persist. New techniques, such as optical interferometry, adaptive optics, and multi-wavelength imaging, continue to sharpen our view. Instruments on telescopes like the Very Large Telescope, VLT, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have begun to pierce the dust veil. Infrared space telescopes, past and present, offer crucial data. But the process is slow, cumulative, and full of caveats. Each new image or data set refines our understanding just a little more, helping to peel back one layer of the mystery surrounding this incredible star. In a way, the difficulty of studying Mu Cephei adds to its allure. It's not just a titan in size, but in secrecy, a quiet colossus hidden behind clouds of its own making, taunting astronomers with every red shimmer. And it's precisely this blend of enormity and elusiveness that ensures Mu Cephei will remain a fascinating object of study for years to come. Infrared astronomy has become one of the most powerful tools for unveiling the secrets of stars like Mu Cephei, stars that are otherwise veiled by thick layers of cosmic dust. When visible light is blocked or scattered, the longer wavelengths of infrared radiation slip through the particles with far less obstruction, allowing astronomers to see what lies beneath the dusty shroud. For a red supergiant such as Mu Cephei, which is ejecting colossal amounts of material and surrounded by a complex cloud of gas and dust, infrared light is the key to unlocking its true structure, behavior, and fate. Mu Cephei radiates across multiple wavelengths, but its outer shell, composed of expelled gas and dust grains, severely hampers optical observation. However, this dust is not simply a nuisance, it's actually quite informative. The particles absorb the star's intense radiation, heat up, and then re-emit that energy in the infrared spectrum. This re-radiated light provides a wealth of information, turning the dust from an obstacle into a source of data. Using infrared telescopes, both ground-based and space-based, astronomers can now peer deeper into the heart of this red supergiant than ever before. The Spitzer Space Telescope, for example, provided early images that revealed Mu Cephei's extended infrared glow, a halo of heated dust swirling far from the stellar surface. These observations help map the star's mass loss history, showing that the surrounding envelope isn't a smooth sphere, but rather a turbulent, clumpy structure where the ejected material varies in density and temperature. This kind of observation would be impossible in visible light. Optical wavelengths are absorbed or scattered by the dust grains, especially those composed of carbon, silicon, or other heavy elements, but infrared radiation, particularly at longer wavelengths, sails right through. By observing the star at different infrared bands, such as near-dash, mid-dash, and far-infrared, astronomers can build a 3D picture of the circumstellar environment, identifying cool outer shells, warmer clumps closer in, and even dynamic changes in those structures over time. Beyond simply seeing through the dust, infrared spectroscopy allows scientists to determine the chemical composition of the expelled material. With instruments like the infrared spectrograph, IRS, on Spitzer or the newer tools aboard the James Webb Space Telescope, JWST, we can detect the spectral fingerprints of molecules and dust grains that tell us exactly what Mu Cephei has been expelling into space: silicates, alumina, water vapor, and complex carbon-rich compounds. These components don't just shape the immediate environment, they'll one day form the seeds of new stars and planets, once Mu Cephei ends its life. Instruments like the JWST's MIRI, mid-infrared instrument, have pushed this field even further, delivering unprecedented resolution and sensitivity in a wavelength range perfectly suited for exploring red supergiants. These observations are particularly useful for studying the inner region of the dust shell, just above the stellar photosphere, where the wind is still accelerating and the gas begins to condense into dust grains. Understanding this boundary, where the dying star meets the emerging nebula, is essential to understanding how mass is lost, how stars like Mu Cephei shape their surroundings, and how they evolve toward their final explosive fate. Another revolutionary contribution of infrared astronomy lies in measuring stellar pulsations more accurately. Mu Cephei is a semi-regular variable star, and while visible light observations have long tracked its brightness fluctuations, infrared data allows scientists to peer deeper into the true physical changes occurring in its outer layers. As the star expands and contracts, the temperature, density, and dust production rate shift in measurable ways, variations that are more cleanly observed in the infrared, where the interfering veil of dust is largely transparent. This capability also allows astronomers to trace changes in mass loss over time. Some red supergiants go through episodic events where the rate of mass loss increases dramatically, possibly triggered by pulsations or convective instabilities. Infrared monitoring of Mu Cephei has shown signs of such events, helping refine stellar evolution models for high-mass stars in their final stages. Infrared astronomy doesn't just benefit from escaping Earth's atmosphere, which absorbs large parts of the infrared spectrum. It also thrives in space-based observatories far above the clouds. However, ground-based infrared observatories have also made critical contributions. Telescopes located at high, dry altitudes, such as those in the Atacama Desert in Chile, have taken advantage of thin atmosphere and low humidity to observe Mu Cephei in the infrared from Earth. Instruments like those on the Very Large Telescope, VLT, and the Subaru telescope use adaptive optics to correct for atmospheric distortion, producing stunning images of the extended stellar halo and the complex structures within the circumstellar envelope. Crucially, infrared interferometry, combining signals from multiple telescopes, is also helping overcome the limitations of angular resolution that affect single-dish telescopes. Observatories like the Chara Array and the VLTI, Very Large Telescope Interferometer, can now simulate a telescope the size of a football field or larger, resolving details in Mu Cephei's atmosphere and outer layers that would otherwise be impossible to detect. Through all these advances, the field of infrared astronomy has revolutionized how we study red supergiants. Without it, Mu Cephei would remain little more than a dim, blurry smudge, its secrets locked away behind layers of dust. But with it, we can now witness the star's inner life, its chaotic surface, its constant shedding of mass, its turbulent envelope, and the intricate dance between light and matter that defines its final days. Infrared astronomy has, in essence, lifted the veil, not entirely, but enough to let us glimpse the grandeur and complexity of Mu Cephei. And as technology continues to improve, we can expect even greater clarity in the years ahead. With each infrared photon we collect, we learn more about what it means for a star to die in beauty, veiled but radiant, mysterious yet eloquent. The launch of the European Space Agency's Gaia mission marked a monumental leap forward in the way we understand the positions, distances, and motions of stars throughout the Milky Way. For a star as massive, mysterious, and crucial to stellar evolution as Mu Cephei, Gaia's precise measurements have provided a much-needed recalibration of its place in the universe. Before Gaia, astronomers relied on more indirect methods, spectroscopic parallax, comparative modeling, and assumptions based on stellar classification, to estimate Mu Cephei's distance from Earth. These approaches, while useful, often led to a wide range of estimates, spanning from as close as 1,500 light-years to over 6,000 light-years. That variance made it incredibly difficult to pin down Mu Cephei's true size, luminosity, and evolutionary status. Gaia changed everything. Gaia is fundamentally a parallax measuring machine. It was designed to map over 1 billion stars in our galaxy by tracking their minute positional shifts as Earth orbits the Sun. This parallax, essentially a cosmic form of triangulation, can reveal with stunning precision how far away each star lies. Even for distant stars like Mu Cephei, where the apparent parallax is incredibly tiny, measured in fractions of milliarcseconds, Gaia's instruments can detect and quantify these shifts with an accuracy never before achieved. When the Gaia Data Release 2, DR2, was published in 2018, it provided one of the most detailed maps of the galaxy to date. While Mu Cephei's extreme luminosity and complex atmospheric environment presented some challenges for Gaia's instruments, especially due to saturation effects and extended dusty envelopes, it still managed to significantly refine our understanding of the star's distance. Based on updated parallax measurements, Mu Cephei is now estimated to be located approximately 2,800 to 3,200 light-years away, a refinement that has helped resolve many of the conflicting estimates from earlier decades. Why does this matter? Because distance is everything when studying a star. The apparent brightness we see from Earth is not a reliable measure of a star's true luminosity unless we know how far away it is. A star may appear faint because it's small and dim, or because it's incredibly far away. By locking down the distance more confidently, Gaia allows astronomers to calculate Mu Cephei's absolute magnitude, and from that, derive its true luminosity, radius, and surface temperature with far greater accuracy. This clarity in distance also ripples outward to influence models of stellar evolution. Knowing how big and bright Mu Cephei truly is helps astrophysicists determine how much mass it has lost, how much remains, and how close it is to a supernova explosion. These figures are essential for predicting the star's future, understanding the timing of its demise, and modeling the physics of other similar red supergiants. Without a precise distance, such models are riddled with uncertainties. With Gaia, we've taken a critical step towards certainty. But Gaia's contributions go even further. It also tracks the proper motion of stars, their movement across the sky relative to more distant background objects. For Mu Cephei, this proper motion data shows that it's not a runaway star nor part of a tight cluster, but rather a solitary giant slowly drifting through the galaxy. This tells us something important about its origins. Unlike some massive stars that are kicked out of stellar nurseries by dynamic interactions, Mu Cephei likely formed in relative isolation or has traveled far from its birthplace over millions of years. That adds nuance to our understanding of how red supergiants evolve outside of dense stellar environments. Another fascinating insight from Gaia is its ability to detect subtle wobbles in a star's motion that may hint at companions or orbital anomalies. While Mu Cephei is not currently known to have a binary companion, Gaia's extended mission may yet uncover hints of gravitational interactions, perhaps with unseen masses or circumstellar structures influencing its trajectory ever so slightly. Gaia's future data releases, especially from its extended mission operations, are expected to deliver even more precise parallax values and proper motion vectors. As the mission continues to observe the sky repeatedly over longer time baselines, its ability to fine-tune distances to bright, complex stars like Mu Cephei will only improve. This means we are on the cusp of even sharper clarity regarding this ancient, massive star's fundamental parameters. In the broader context, Mu Cephei is just one of many red supergiants that Gaia is helping to define more precisely. Its contributions to the mapping of the Milky Way are reshaping our understanding of stellar populations, galactic structure, and the life cycles of the most massive stars. But for Mu Cephei in particular, Gaia has done something quite profound. It has allowed this veiled giant, once shrouded in uncertainty and myth, to be placed more firmly and accurately within the grand tapestry of the cosmos. It's astonishing to think that by measuring a star's minuscule positional wobble, fractions of a hair's width at the distance of the Moon, we've been able to recalibrate our entire perception of its size, luminosity, and significance. Thanks to Gaia, we now view Mu Cephei not through a lens of speculation, but with data-backed reverence. It is no longer a ghostly ember in the dark. It is a measured entity, majestic in size and nearing its end, ready to teach us what it means to die as a star. Mu Cephei's place in the cosmic story is not merely as a spectacle of color or size. It is a critical key to understanding how the most massive stars in our universe live, age, and ultimately die. It is a living laboratory, a grand finale frozen in slow motion, revealing the intricate and violent processes that shape stellar evolution on the most colossal scale. Massive stars like Mu Cephei evolve very differently from smaller stars such as our Sun. From their very birth, they burn brighter, live faster, and die more dramatically. Mu Cephei began its life millions of years ago, far younger than our 4.6 billion-year-old Sun, but it has already exhausted the primary fuel at its core, hydrogen, and now teeters on the edge of its final fate. This rapid life cycle, though fleeting on a cosmic timeline, is rich with transformational physics that can only be studied in real time by observing stars at each phase. Mu Cephei is firmly in the late red supergiant phase, a point few stars ever reach, and this gives us a rare opportunity to see what happens during the closing chapters of a massive star's existence. One of the most significant lessons Mu Cephei offers lies in mass loss and envelope instability. Red supergiants are known to shed vast amounts of their outer material into space through intense stellar winds. Mu Cephei is doing exactly this, throwing off shells of gas and dust that now form a thick, veiling nebula around it. The study of this material, especially with infrared and submillimeter telescopes, provides insights into how red supergiants enrich the interstellar medium with heavier elements. These elements, carbon, oxygen, silicon, even iron, are the building blocks for future generations of stars, planets, and life. In essence, Mu Cephei is a stellar forge, producing and distributing the raw ingredients of the universe. This process is not simply poetic, it is physical, chemical, and absolutely vital to galactic ecology. More specifically, Mu Cephei helps researchers explore the thresholds that lead to core collapse supernovae. As it stands, the internal core of Mu Cephei is no longer fusing hydrogen. It has progressed through helium fusion and may already be fusing heavier elements like carbon, neon, and oxygen. This core burning sequence proceeds like a cascade, each step shorter than the last, until the star begins producing iron. Iron fusion requires more energy than it releases, leading to a gravitational collapse that triggers a supernova. The mass, composition, and core structure of Mu Cephei are under close scrutiny, as understanding its specific stage helps fine-tune theoretical models of this entire collapse sequence. Another important contribution of Mu Cephei to the science of stellar evolution is the opportunity to study instabilities and pulsations in late-stage stellar interiors. These pulsations, which cause the star to vary in brightness and expand or contract slightly, are surface echoes of deep internal changes. Tracking the pulsation periods and amplitude shifts over time gives astronomers a unique diagnostic tool. It's almost like an electrocardiogram of the star's heart, offering clues to the health and progression of its nuclear core. The fact that Mu Cephei is a semi-regular variable further enhances its scientific value. It serves as a bridge between stars with predictable periodicity and those with chaotic or stochastic variation, offering insight into the transition between order and chaos in dying stars. Moreover, Mu Cephei's immense size and luminosity make it an excellent test subject for refining stellar evolution codes and simulations. Computer models must account for how convection operates in such huge outer layers, how radiation escapes through dusty envelopes, and how these layers interact with deeper fusion zones. The sheer scale of Mu Cephei pushes the limits of these simulations, revealing where our understanding is solid and where it falters. Discrepancies between observation and theory often lead to better models, more accurate physics, and ultimately a deeper comprehension of the life cycles of massive stars. It also helps illuminate the transition between supergiant phases. While stars can evolve from main sequence to red supergiant status relatively quickly, the path from red supergiant to supernova is still not entirely clear. Some red supergiants shrink and heat up before exploding, passing through a yellow or blue supergiant phase. Others seem to retain their bloated red size right up to the moment of collapse. Whether Mu Cephei will change color and size again before it detonates, or remain as it is still a mystery, but it's a mystery scientists are actively trying to solve by watching this star closely, year after year. Beyond its role as a red supergiant case study, Mu Cephei helps complete the broader stellar narrative by demonstrating the upper boundaries of stellar size and behavior. It's a reminder of what massive stars can become, and of what happens when nuclear fuel can no longer support a massive gravitational load. The violent, luminous death of stars like Mu Cephei does more than end a stellar life. It seeds the galaxy with energy, momentum, and matter. The shockwaves from such events can trigger star formation in nearby clouds, while the elements they eject enrich those new stars and planets. In this sense, Mu Cephei is not just showing us how stars die, it's showing us how the galaxy renews itself. In summary, Mu Cephei is not merely a red beacon in the sky, it is a chapter in the grand book of stellar evolution. It tells us about internal fusion, external winds, pulsating layers, collapsing cores, and dust-filled atmospheres. It tells us that endings are not endings at all, but transitions to new beginnings. Every gram of matter it sheds is a promise of future stars, future worlds, and perhaps even future life. For scientists, it is a crucial piece of a cosmic puzzle. For everyone else, it is a reminder that even death in the universe is beautiful, creative, and essential. Mu Cephei is a colossus by nearly every standard we can imagine. When we hear that a single star could be over 1,000 times the radius of our Sun, it's almost too vast to comprehend. If it were placed where our Sun currently resides, it would swallow Mercury, Venus, Earth, Mars, and likely reach the orbit of Saturn. It's no wonder, then, that many often assume Mu Cephei to be the largest star in the universe. But while Mu Cephei certainly ranks among the most massive and voluminous, it does not claim the crown of the largest known star. In fact, it stands just shy of that title, still spectacular, but edged out by a few extreme outliers in the stellar zoo. To understand Mu Cephei's true place among the giants, we must carefully examine what it means to be the largest. In astronomy, we typically talk about three different ways to measure stars: mass, luminosity, and radius. When we say Mu Cephei is not the largest, we are primarily referring to radius, its sheer size in terms of physical volume. Mu Cephei's estimated radius hovers around 1,260 to 1,650 times that of the Sun, depending on which measurement technique and assumptions about distance are used. That alone is mind-boggling. But this estimate puts it in competition with a handful of extreme red supergiants and hypergiants, whose dimensions seem almost surreal. Among them, Ui Scuti, Vy Canis Majoris, WOHG 64, and Stephenson 2-18 have often been cited as stars that surpass Mu Cephei in physical diameter. Let's take Ui Scuti as a point of comparison. Ui Scuti has been estimated to be over 1,700 times the Sun's radius. If accurate, that would make it the current record holder for the largest known star by radius. But here's the important caveat: these measurements come with enormous uncertainties. For distant, bloated red supergiants like Mu Cephei or Ui Scuti, exact sizes are hard to pin down due to variable brightness, dense outer layers, and uncertain distances. Even slight errors in parallax or assumptions about dust can translate into massive differences in calculated size. Despite these uncertainties, the data suggests that Mu Cephei is just slightly smaller in radius than these other giants. This doesn't make it any less magnificent, but it places it just off the top of the leaderboard. Yet interestingly, Mu Cephei tends to stand out more in public recognition because of its distinctive color and visibility. While Uyscuti and others are buried in denser star fields or obscured regions of the galaxy, Mu Cephei shines clearly in the northern sky and has been admired for centuries. Its visibility to the naked eye makes it a favorite among both amateur and professional astronomers. It's also worth noting that largest does not always equate to most massive. Mu Cephei is certainly a heavyweight. It's believed to have started its life with somewhere between 25 to 40 solar masses, though it has lost a good portion of that through stellar winds. In contrast, our 136A1, while not as large in volume, is more massive, currently believed to weigh over 200 solar masses, the most massive star we know. So while Mu Cephei is among the largest by diameter, there are stars far denser and more massive. Moreover, the reason Mu Cephei and others can become so large in physical size, despite being less massive than some compact stars, has to do with their internal structure and late-stage evolution. As red supergiants, they have very low surface gravity in their outer layers. The energy generated in their cores pushes outward, puffing up the star's atmosphere until it becomes extended and tenuous. These outer layers are so loosely bound that they behave more like a cloud than a solid body, making the star appear vastly larger than its mass might suggest. Another important factor to consider is the shape and structure of these stars. They are not perfect spheres. Due to their slow rotation and large convective envelopes, red supergiants like Mu Cephei can have irregular shapes, lopsided mass distribution, and even large convection cells that alter their visible radius at different times and angles. This means the concept of radius becomes more of an average than an exact measurement. So when we compare Mu Cephei to Uyscuti or Vy Canis Majoris, we're not necessarily comparing uniform spheres, we're comparing dynamic, unstable, semi-transparent clouds of glowing plasma. So what does it mean, then, for Mu Cephei to be not quite the largest? It means that, in a universe filled with strange and wondrous objects, it is one of the most dramatic and awe-inspiring, just not the single record holder. But its elegance lies in more than just measurements. It stands among the largest, brightest, and most colorful stars visible to the naked eye. It is a living demonstration of what stars can become at the end of their lives, a lesson in extremity, in fragility, and in scale. Being the second or third largest doesn't make it any less important. On the contrary, Mu Cephei's well-observed characteristics, coupled with its accessibility from Earth, may make it more scientifically valuable than even the technically bigger stars that are harder to study. It's also worth celebrating that Mu Cephei, despite not being the largest, is often one of the most photogenic stars through telescopes. Its red glow stands out vividly against the black canvas of space, making it an icon among celestial objects. The nickname, the Garnet Star, evokes not just its hue but its unique beauty. Among stars, being legendary is perhaps more meaningful than being the largest. In the end, whether it's ranked second, third, or fifth in radius, Mu Cephei is indisputably a titan of the cosmos, a representative of one of the rarest and most powerful phases a star can go through. And while some stars may technically be larger, few command the same attention or stir the same awe in observers both amateur and professional alike. Mu Cephei is more than just a star, it's a symbol of cosmic grandeur at the edge of its own existence. Every moment it shines is a testament not only to the titanic energies burning within, but also to the slow, sorrowful inevitability of its decay. Like the final act of a grand symphony, its brilliance in the night sky is tempered with melancholy. Mu Cephei is dying, and has been for tens of thousands of years. Yet its death is not sudden, not explosive, at least not yet. It is slow, majestic, and patient, like a fading ember that once blazed with the fire of creation. To understand this dying light, we must peer into the very soul of what it means to be a red supergiant. Stars like Mu Cephei do not fade gently into the night as smaller stars do. They do not become stable white dwarfs or planetary nebulae. Instead, they march toward a much more violent fate, one born of unstoppable gravitational collapse. But long before that catastrophic end arrives, they undergo changes so immense and violent that they seem almost biblical in scale. Mu Cephei is currently in the helium-burning phase of its life, having already exhausted the core supply of hydrogen that sustained it for millions of years. Deep within its heart, helium atoms are fusing into heavier elements such as carbon and oxygen. Around the core, shells of hydrogen continue to burn, layered like the concentric rings of a tree. But this fusion isn't as stable or as efficient as hydrogen fusion, and as heavier elements are created, fusion becomes increasingly difficult to sustain. As the internal pressure from fusion wanes, gravity begins to gain the upper hand. The star compensates by expanding even further, puffing out its outer layers to maintain equilibrium, which explains Mu Cephei's enormous radius. However, these vast outer layers are not tightly bound. They are so diffuse that many particles are barely gravitationally connected to the core. As a result, the star is losing mass rapidly in the form of stellar winds, powerful outflows of gas and dust that drift into space, creating a halo of material around it. This is the light of a star in the twilight of its life, beautiful, but unstable. The very color of Mu Cephei speaks to its old age. The rich red hue that earned it the name, the Garnet Star, is a result of its cool surface temperature, approximately 3,700 Kelvin. That low temperature is not due to weakness, but to size. The energy it generates is immense, but it is spread across such a vast surface area that the outer envelope glows more like a coal than a flame. Red supergiants are, paradoxically, some of the most luminous and yet coolest stars we know. Mu Cephei is both powerful and frail, a cosmic contradiction wrapped in crimson. What makes Mu Cephei's decline so haunting is the timescale. Human lives are mere flickers compared to the lifespans of stars, and yet, in stellar terms, Mu Cephei is in its final breath. Astronomers believe it has only a few 100,000 years left, perhaps even less. For a star that may have lived 10 million years or more, that is the equivalent of the final seconds before midnight. The countdown has begun. The engines that fueled it are winding down. The materials for its final act are assembling quietly, deep in the core. Within that core, fusion reactions are building heavier and heavier elements: carbon, neon, magnesium, silicon, eventually reaching iron. Iron is the end of the line for stellar fusion. It cannot release energy through fusion like lighter elements do. When iron builds up to a critical point, it spells doom. Gravity will win at last, pulling the star's core inward in a fraction of a second, collapsing it into an unimaginably dense state. That is the moment when death becomes transformation, when the red supergiant becomes a supernova. But we are not there yet. Mu Cephei still stands on the precipice of collapse. It still pulses, breathes, and glows. Its outer layers shimmer with the faint beat of instability. Astronomers observe this variability, these fluctuations in brightness, and know they are watching a slow unraveling of a stellar soul. It is a long goodbye. A fading beacon in a dark and vast universe. There's a kind of cosmic poetry in knowing that Mu Cephei is nearing the end. Every photon that reaches our eyes from the Garnet Star began its journey thousands of years ago. We are not seeing it as it is, we are seeing it as it was, long before the rise of human civilization. By the time its light reaches us, its story has already moved forward in ways we cannot yet see. It may be larger now, dimmer, redder, more unstable. It may even be gone, its final light racing toward us through the abyss of space. One day, perhaps one clear night, the sky will erupt with a light we've never seen before, the final flash of a star's farewell. But even if Mu Cephei were to collapse tomorrow, the light of its death would not reach us for thousands of years. Until then, it remains perched on the celestial stage, still performing, still gleaming. A cosmic relic, an ancient monument to the relentless forward march of time and entropy. A reminder that even the most titanic of stars cannot escape the fate written into their atoms. And yet, in that fate, there is beauty. For the death of a star is not an ending in the way we understand it. When Mu Cephei dies, it will become the seed of new creation. Its shattered remains will enrich the galaxy with elements like carbon, oxygen, and iron, materials necessary for planets, for oceans, for life. In dying it gives. In fading it empowers the birth of other worlds. Its death will not be a disappearance, but a transformation. That is why the dying light of Mu Cephei isn't just sad, it is sacred. It is a silent prophecy written in starlight, foretelling the renewal of galaxies. We watch it with awe not because it is fading, but because of what its fading means. It is a final flare, not into darkness, but into legacy. When Mu Cephei eventually meets its dramatic end, the result will be one of the most awe-inspiring events the universe has to offer, a supernova. This isn't just a flashy conclusion to a long life, it's the ultimate transformation of matter and energy. A supernova of a red supergiant like Mu Cephei is not subtle. It would be so powerful, so luminous, so spectacular, that it would literally outshine the entire galaxy, for a brief but unforgettable time. Let's imagine what such an explosion would look like, how it would affect us on Earth, and what mysteries it might reveal in its violent farewell. First, let's consider the spectacle. When Mu Cephei explodes, the outer layers of the star will be violently thrown into space, moving at speeds of up to 10,000 kilometers per second. The core, no longer supported by fusion pressure, will collapse in a fraction of a second, potentially becoming a neutron star or black hole. That collapse releases a staggering amount of energy, more than the Sun will emit in its entire 10 billion year lifetime. Most of this energy will come in the form of neutrinos, tiny, nearly massless particles that blast out of the collapsing core in all directions. However, what we see from Earth will be light, blinding, burning, searing light that carries the final signature of this mighty stellar titan. If Mu Cephei exploded tonight, its light wouldn't reach us for around 2,800 years. That's because the star is about 2,800 light-years away from Earth, meaning everything we observe from it is already ancient history. So, even if the star has already exploded, we would still be completely unaware. But once the light does arrive, whether it's tomorrow, or in 1,000 years, the entire sky will briefly change. At its peak, the supernova could rival, or even surpass the brightness of the full moon, though it would appear as a single, intensely brilliant point of light. It would likely be visible in broad daylight for weeks, possibly even months. At night, it would dominate the sky, casting shadows, drawing the gaze of billions, and forever altering the way we understand our place in the cosmos. Unlike a planet or a star, a supernova is not steady. Its brightness rapidly increases over days, peaks, and then gradually fades over months. For amateur astronomers and scientists alike, it would be the observation opportunity of a lifetime, an event no one alive has ever seen up close in our own galaxy. Historically, the last time humans witnessed a naked-eye supernova in the Milky Way was in 1604, when Johannes Kepler recorded the explosion of a star in the constellation Ophiuchus. That event was so bright it could be seen during the day, and it became a key moment in the development of modern astronomy. The explosion of Mu Cephei would dwarf even that. In fact, a supernova of this magnitude would likely trigger worldwide fascination, and perhaps even panic among those who don't understand what's happening. It's no exaggeration to say that every news outlet on Earth would cover it, and millions of people would turn their eyes skyward each night. And what a sight it would be! The light from a Type II supernova, what Mu Cephei would likely become, arrives with a broad spectrum of radiation. It starts with a sharp shock breakout, a sudden, bright flash of ultraviolet and X-ray radiation as the core collapse triggers a shock wave that races through the star and erupts from its surface. Within hours to days, the optical light ramps up, glowing hotter than nearly any object in the universe. For a few brief days or weeks, Mu Cephei could appear brighter than all other stars in the night sky combined. This light carries with it fingerprints, spectral lines, that tell astronomers exactly what elements are being thrown into space. Hydrogen lines would dominate the early spectra, followed by heavier elements like helium, oxygen, carbon, calcium, and iron. These are the building blocks of life, forged in the belly of the dying star and scattered like cosmic seeds into the galaxy. By studying this light, scientists could learn about the internal structure of Mu Cephei in its final moments, almost like performing a cosmic autopsy. But light isn't the only thing we would detect. Instruments on Earth, particularly neutrino detectors like Japan's Super Cameo Candy or the IceCube Neutrino Observatory in Antarctica, would register an immense spike in neutrinos. These ghostly particles would arrive before the light does, because they pass straight through matter unimpeded while photons bounce and scatter through the expanding cloud of gas. The arrival of this neutrino burst would serve as the first alarm bell, signaling that something incredible has just occurred in the cosmos. Then comes the gravitational wave. If the collapse of Mu Cephei's core is not perfectly symmetrical, and it likely wouldn't be, it would produce ripples in the fabric of spacetime itself. Detectors like LIGO and Virgo could pick up this signal, offering a direct measurement of the violence unfolding at the star's heart. A detection like this would be invaluable, giving scientists their first detailed look into the inner collapse of a massive star in real time. Even after the light show fades, Mu Cephei's explosion will leave behind a nebula of expanding gas and dust, a supernova remnant glowing with shock-heated material and bathed in X-rays. This remnant will remain visible for centuries, growing and evolving as it interacts with the surrounding interstellar medium. The Crab Nebula is the remnant of a supernova from 1054 AD, and it's still one of the most studied objects in the sky. Mu Cephei's remnant would become another enduring monument in the heavens, a glowing scar where a titan once lived. Importantly, despite its dramatic appearance, Mu Cephei's supernova wouldn't pose a threat to Earth. While some supernovae can damage nearby planetary systems with intense radiation or high-energy particles, Mu Cephei is far enough away, over 2,800 light-years, to spare us from those dangers. At that distance, the only impact we'd feel would be psychological and scientific. It would be an event to remember, not one to fear. Still, the philosophical implications of such an event are hard to ignore. We often think of the stars as eternal, but they are not. They are born, they live, and they die. Mu Cephei's death would serve as a powerful reminder that the cosmos is alive with change, beautiful, violent, and necessary change. Just as our sun will one day exhaust its fuel and transform, so too does every other star in the sky. Mu Cephei is simply ahead of the curve. Its explosion would also highlight the interconnectedness of the universe. The elements forged in its core, oxygen for our lungs, calcium for our bones, iron for our blood, will one day drift through the galaxy, perhaps becoming part of new stars, new planets, and perhaps even new life. In that sense, its death is not just an ending, but a transformation. A continuation of the cycle that links stars, planets, and people. For all our scientific understanding, we cannot predict exactly when Mu Cephei will explode. It could be tomorrow or 100,000 years from now. But it will happen. That is certain. And when it does, the universe will watch. Earth will watch. And humanity, perhaps for the first time in centuries, will be united by the shared experience of witnessing a star's death. There is something deeply poetic about that, about a dying star binding together a living world. Perhaps when that day comes, we'll remember to look up. Perhaps we'll remember that we come from stars, and that their stories are, in some way, our stories too. The universe is a vast, ever-evolving cycle of creation and destruction, where the death of one celestial object often gives birth to many others. Nowhere is this more poetically evident than in the fate of stars like Mu Cephei. As massive and powerful as it is, Mu Cephei is not immortal. But in its final act, its decay, its explosion, it contributes to something far greater than itself. It gives back to the cosmos. It seeds life. This is the beauty of cosmic decay. When Mu Cephei eventually reaches the end of its life and explodes in a supernova, the event will be unimaginably violent and luminous. But it will also be immensely productive. That explosion will not simply be the end of a single star. It will be the dispersal of countless elements across light years of space, elements that were forged over millions of years in the crucible of Mu Cephei's core. These are not just arbitrary substances. These are the elements that make up everything we know. Before it explodes, Mu Cephei is already working to reshape the cosmos. In its red supergiant phase, it's shedding mass through powerful stellar winds. These winds carry carbon, nitrogen, oxygen, silicon, and other heavy elements out into space. Over thousands of years, Mu Cephei has been surrounded by a growing envelope of gas and dust, a kind of pre-supernova offering to the galaxy. This dust doesn't disappear. It floats through the interstellar medium, enriching it, thickening it, altering its chemical makeup in invisible but profound ways. Then comes the final explosion, the supernova. In a moment, Mu Cephei will forge even heavier elements, iron, nickel, cobalt, and possibly trace amounts of gold and uranium. These materials, created only in the intense pressures and temperatures of a supernova, will be hurled into the void. Shockwaves from the explosion will plow into the surrounding gas and dust, compressing clouds of material that were once floating passively. This compression will cause gravitational collapse. And that collapse can spark new birth. From the debris of Mu Cephei, new stars will form. It's one of the great ironies of the universe, that death is necessary for rebirth. Massive stars like Mu Cephei are both destroyers and creators. Their deaths are violent, but their legacy is regenerative. They are the reason the universe has evolved from a simple soup of hydrogen and helium into the complex, chemically rich cosmos we see today. Every rocky planet, every life form, every human being, owes their existence to the death of stars like this one. When a star like Mu Cephei dies, it doesn't vanish. Its mass, its atoms, its energy, all of it is conserved, transformed, and redistributed. What once was core and mantle becomes nebula. What once radiated as starlight becomes dust and molecules. These components drift through space, sometimes for millions of years, until they encounter regions dense enough to trigger gravitational collapse once more. There, they may form a new star, or even a solar system. Perhaps one of those new systems will host a rocky planet. And perhaps, just perhaps, life will eventually emerge there. The star's legacy doesn't end with atoms. The photons Mu Cephei emitted in its lifetime have already traveled across interstellar space, warming nearby clouds, altering chemistry, helping shape molecules that drift within future star-forming regions. Even in its final act, its supernova explosion, it emits energy that can influence the chemistry of nearby gas clouds. This radiation can ionize hydrogen, catalyze the formation of complex organic molecules, and help trigger the formation of protoplanetary disks. And there's more. The dust produced by Mu Cephei's death is the very dust we find in meteorites on Earth. It's the same stardust trapped in ice cores in the polar regions. It's the grains found in ancient lunar soil. These are not metaphors, they are literal pieces of dead stars. Tiny particles that drifted across vast distances of space before being captured by Earth's gravity. In laboratories, scientists have isolated microscopic grains of stardust, each one older than the solar system itself, each one a fingerprint of a red supergiant's final breath. Imagine, then, what might come from Mu Cephei's final breath. 1,000,000 years from now, its remnants may become part of a newborn solar system. That system may one day develop planets. And those planets may one day develop intelligent life. That future intelligence might look up at their night sky and discover remnants of the supernova that birthed them. They may study its remnants, its expanding shell, its chemical signature, and realize they are children of a dead star. The circle will have completed itself once more. But even closer to home, Mu Cephei's death will provide insight and inspiration. Astronomers will use the data from its supernova to refine models of stellar evolution, nucleosynthesis, and galaxy formation. The explosion may even reveal unknowns, perhaps exotic physics in the core collapse, or new classes of neutrino behavior, or insights into gravitational waves. In this way, the star's death does not just create matter, it creates knowledge. It expands the boundary of human understanding. The universe is not static. It breathes. Stars like Mu Cephei are its lungs. They inhale hydrogen, fuse it into heavier elements, and eventually exhale those elements in fire. That breath becomes everything else. That is cosmic decay, not an end, but a transition. A sacred exchange in which destruction begets creation. So when we think of Mu Cephei's final chapter, we should not mourn it. We should celebrate it. Its death will ripple through space and time, shaping futures that no one can predict. Its elements will form the backbone of countless new stars and planets. Its light will shine long after it's gone, echoing through the galaxy in starlight, nebulae, and life itself. It is this cycle, this cosmic recycling, that defines the universe as a living, evolving entity. Mu Cephei will leave no tombstone. Instead, it will leave galaxies blooming with stars. It will leave science richer, space more complex, and existence more profound. Its death will not be a conclusion. It will be a beginning. In the vastness of the cosmos, where galaxies spin like pinwheels of fire and black holes lurk in the unseen corners of spacetime, Mu Cephei stands as a luminous sentinel, a glowing ember of time, burning slowly in the depths of the constellation Cepheus. As we arrive at the final reflection on this magnificent star, we must confront not just its physical grandeur or scientific significance, but something far more profound, its symbolism. Mu Cephei is not merely a red supergiant, nor is it simply a candidate for a future supernova. It is a monument to the cosmos itself, a manifestation of both power and fragility. It is a living chronicle of the universe's most dramatic processes, a reminder that even the mightiest things are not immortal. From Earth, we see it as a speck of crimson light, faint to the naked eye but immense in nature. That light has traveled for thousands of years to reach us. Each photon escaping its outer layers carries the story of nuclear fusion deep within. Those photons are ancient messengers, telling tales of pressure, gravity, instability, and time. When we look up at Mu Cephei, we're not just seeing a star, we're peering into deep time. Into a chapter of cosmic history that began long before humans ever looked toward the sky and wondered. The nickname, the Garnet Star, given by William Herschel, was no casual label, it was poetry. Herschel saw in Mu Cephei not just a light in the sky, but a hue so rare and beautiful it demanded to be named. He recognized, even in the 18th century, that this was no ordinary star. Its deep, rich red color wasn't just a scientific oddity, it was a visual sonnet, a spectral echo of the elemental fire burning in its vast heart. In an age before high-resolution telescopes, before spectroscopy and space observatories, Mu Cephei captured the imagination. It continues to do so today, but with even deeper resonance, because now we know more about what it truly is, and that knowledge only deepens the awe. Mu Cephei is a supergiant, yes, but even that word feels inadequate. 1,000 times the radius of our Sun, it could swallow entire planetary systems in its convective, roiling atmosphere. It pulses, it dims, it brightens, not with the flicker of instability, but with the slow, tidal breath of a giant nearing the end of its long journey. Its outer layers billow like the folds of a dying flame, shedding material that will one day become the cradle of new cosmic structures. It is vast beyond comprehension, yet transient in the grand scheme of the cosmos. A paradox. A colossus with an expiration date. It is, at its core, a star that reminds us of the dual truths that define everything in the universe, impermanence and transformation. Mu Cephei, like all red supergiants, was once a main sequence star not so different from our own Sun, only vastly more massive. It burned through its hydrogen quickly, hungrily, as giants do. And now it fuses heavier elements, layer by layer, marching toward an inevitable collapse. But that collapse is not failure. It is fulfillment. Its destiny is not to fizzle out, but to go out in a blaze of creation, a supernova, a rebirth of matter and energy. And that brings us to the human perspective, because for all the science, all the data, and all the models we've discussed, there is still something elemental about how Mu Cephei makes us feel. This star, so distant, so unlike anything we could ever touch or stand upon, somehow inspires awe that is profoundly intimate. It reminds us of our smallness, yes, but also of our connection to everything. As Carl Sagan once said, "We are made of star stuff." And Mu Cephei is that stuff, unfolding before our eyes. The iron in our blood, the oxygen in our lungs, the calcium in our bones, all of it once came from stars like Mu Cephei. Long ago, red supergiants exploded and scattered their essence into the void. That dust, that ash of dying suns, condensed to form new solar systems. Ours was one of them. The atoms in your body have passed through the hearts of stars. That is not just poetic, it is scientifically true. You are, in the most literal way, a child of cosmic decay. And Mu Cephei is your ancestor. Yet this is not the end of its story. Not yet. At this very moment, it continues to burn, to shed its layers, to pulse with internal gravity waves and convection storms that span entire solar systems in width. It continues to change. And in doing so, it teaches us. Every new observation, every light curve, every spectrum taken from its flickering red glow adds to our understanding not just of stellar life cycles, but of the galaxy's evolution. It offers a glimpse into our own past, and a preview of our sun's distant future. Indeed, while Mu Cephei is far more massive than the sun, it follows a path that all stars must walk. It is a mirror held up to the cosmos, showing us what becomes of brilliance. That even something so radiant, so powerful, must eventually surrender to gravity and entropy. But in that surrender lies purpose, meaning, beauty. Its death will be a transformation, not an end. And in that transformation, it becomes more than a star, it becomes a part of everything. And so we must ask, how do we remember a star? We cannot preserve it. We cannot visit it. It is not a monument of stone or steel, but of plasma and light. Its memory is written in the particles it will leave behind, in the data recorded by telescopes, in the imagination of poets, and in the molecules that will one day form new worlds. Mu Cephei's legacy will be scattered across the universe, encoded in dust grains, nebulae, and the dreams of civilizations yet to exist. To look at Mu Cephei is to witness time on a scale we rarely comprehend. It is to understand that existence is fleeting, and that greatness, true greatness, often lies not in how long something lasts, but in how profoundly it changes the world around it. Mu Cephei will change the galaxy. That is not a matter of speculation, but of certainty. The only question is when. And when it does, when the sky is suddenly alight with the final, blazing heartbeat of this ancient red titan, humanity will look up. Telescopes will turn. Eyes will widen. And we will witness a cosmic eulogy millions of years in the making. In that moment, we will not just be watching the end of a star. We will be watching the universe write the next chapter of itself. So, let us remember Mu Cephei not merely as a star, but as a story. A story that began long before us, and will continue long after we are gone. A story of birth, transformation, decay, and rebirth. A story of light, of fire, of dust. A story of fragility, and yet, one of unimaginable strength. In the darkness of Cepheus it burns. Quietly. Patiently. Beautifully. Awaiting its final act. A garnet in the blackness. A monument to the cosmos. A star to remember. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.